Hello? Hello?
Okay. Bhumika, can you hear? Let me take it off mine here. Can you hear now? Let me know if you're. Yes, yes, great. Great, 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 great. Are you? Can you hear on the stream? Jess, go there and try again. Turn it on and try again.
Hi, I'm testing the fuzzy microphone and walking up the stairs. I'm going to walk over here, I'm going to continue onto the microphone, and I'm going to keep talking. And now I'm in the microphone and I'm talking. Hello, this is more testing of sound. Please stand by. Stand by for sound testing. Testing of sound. We're testing this microphone, which I know works, and then the live stream microphone, which is this fuzzy boy. Make your friends watch the live stream, or not make your friends, but like strongly suggest that your friends watch the live stream. I think it would be fun. Why not? What are you doing on like a Friday? Working? Of course not. Why would you do that? I'm not working. Working hard or hardly working, that's what they say. Working hard or sleep deprived, that's what I also say. Yeah, okay. One brain cell is like still in NorCal, and one brain cell has made its way over here, but it needs breakfast. Donnie, how's it? She can't hear me anymore? She can? Yes. Okay. This is a one-way thing. I can't hear you. What's up?
She said she can't hear you, but the quality is not good, so I'm trying to figure that out.
Do you want me to just hold it? Is it like the way I clipped it? I can go like this. Is this any better?
Put it closer, like here.
Yeah, I had it there.
Which was that?
Yeah. Fuck. This. Now I'm back on.
Yes, it says 0.
Hello, I'm talking.
Decrease the volume a little bit.
Okay. Hiya? Okay.
Check. Check 1 2. 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 I'm all the way at the other end of the stage now. All good?
Okay, second test. Test, test.
Testing, testing. Check 1 2 1 2.
now I can hear you. Just when you press one,
But I don't know when it is, Rosie.
me neither. Just trust you.
Hello,
I
hello,
can
hello.
hear.
Oh, okay.
So unmute. No, in this case, mute.
All right, can you hear me? Hi. Hi, I'm gonna put it up one louder. Testing, testing. I'm now talking into the microphone. I'm testing, talking. Great. Okay. So, hello everyone. Welcome to the first inaugural first year of Far Out. Thank you all for coming. Behold. My name is Jess Kuleshov. I am the logistics lead. That's where it's at. Far Out, if you don't know, stands for Friends of Amateur Rocketry Oxidizers Uninhibited Tournament, which I came up with for the record, so you're welcome. Let's go through like a long list of thank yous. So, you know, a million thanks to Mojave Air and Spaceport for providing Conference Center, for setting the tables, for getting these cool, like these colors change on the numbers on the tables, kind of fun, with a remote, kind of fun. But they have basically helped us a lot with connecting with caterers and finding sponsors through tenants at the site and all sorts of like logistical things that we need to get done, helping put on this conference and setting tables, anything in between, ice chests, you name it. Lynn and Nicole have done an amazing job, and all the other folks at Mojave Air and Spaceport. So thanks to them. Yay. Thank you to our general sponsors for trusting such an event from the start. We have Impulse will be here a little bit later. Vast is here now. They're back there. Ursa Major. Waste Management has donated dumpsters. I love them. So I was like, I'm gonna proudly put that on there. And Stratolaunch. So thanks to our sponsors as well for giving us money. All right. After that, thanks to you guys for trusting this competition and coming out here, taking time out of your days. The people who aren't here are doing their finals. Oops, I didn't realize that it was finals week for California people. So they'll be here during the weekend. But thank you guys for trusting us, and thank you to your schools as well for trusting and funding most of your stuff out here if you filled out waivers. If you didn't, I'm sorry. Okay, and then thanks to FAR folks and all the volunteers for volunteering your time. You're not getting paid for this, neither am I. So thanks for being here, and thanks for coming out, spectators. I think that's the list, and if I missed anyone, I'm sorry. Okay, so generally ground rules going forward. Number 1, no discrimination of any sort. I don't want to hear it. Be like race, gender, sexual orientation, politics, religion, any of it. You're coming from different places. You have different views on things. Be respectful. These are your friends. These are people you want to learn from. You have other teams here that you won't get to always talk to. You can talk over Discord all you want, but really talking to somebody and understanding where they're coming from and being respectful of however they came to their decision is important, and you should think about that. If you see something from a student or a spectator, you report it to the nearest volunteer. It will get to me and we'll handle it. If you hear something about a volunteer, you please report directly to me, and then we can handle that as well. So please think about it. Maintain professionality, more of the same. We're casual here. We're all friends to a point. Don't say anything insulting. If you're near a camera, don't say anything terrible. Or you know, like I know that at other competitions, people have not realized that they are on a hot mic and saying things behind the thing. So just maintain professionality. If you see something, say something. This goes across everything. We're all looking out for each other here in a lot of different ways. Out at the site, if you see something that you might think is concerning about another team's setup or something like that, you come to a volunteer and just be like, hey, I think there's something wrong. It's okay to say it. It's not anything like say it in good faith, but do let us know, even if you feel a little bit uncomfortable, because our number one thing is safety out there. We want you guys to do things safely, and we want you to do it right. We will come and ask questions. We're looking ourselves, but basically, if you see anything that seems a little bit out of place, this is the first year of this competition. We want it to go well, and we want people to trust it enough to be able to be like, oh yeah, I'll come to that next year, and that kind of thing. So you see something, you say something. Same thing for looking out for each other. It's hot. This is more for folks like out of the site. It's hot. It has just started being hot out here. It is dry, and you are going to be dehydrated a lot faster than you think. Unfortunately, we kind of have a record at like every rocketry competition, at least one person has heat exhaustion. That's just how it shakes out. Try not to make it you. Make sure that you have one other person that you are looking at, and they are your person that you will go to, and you'll be like, hey, you're looking a little If you think you have heat exhaustion, and we'll talk about it later as well during like safety meetings, stuff like that, but if you think you're already dehydrated, you're way past it. So drink a lot of water. We will have free water out there. We'll have heavily discounted, barely marked up Costco goods for you guys to have as well. And Gatorades. Make sure you bring some powder yourselves, and just, stay cool. Stay communicative as well. Anything you find at all, and this is just down the list, let somebody know so that it doesn't die somewhere and a problem becomes larger than it has to be. Also, wear your badges at all times. You should have gotten them in your bags. So please wear them so that I know that you're part of this. Especially out at the site. Here it's okay, I kind of can understand who's who because I've kind of memorized your faces. But you want to, for volunteers as well, you want to know who you are, you want to know status of kind of things. We don't want random people kind of like boop, 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 coming in. That would be bad. Don't do that. Okay, questions to the end, I suppose. General order of event for today. Oops, the schedule is kind of but that's okay. We'll have a safety meeting right after this, and we'll talk about safety at the site, stuff like that. This will be team of safety leads, but because we've got plenty of folks, you all can hear it and you all benefit from it. We'll have speakers today. They're coming in, it'll be great. We'll have Kevin Miller, who's the VP of Propulsion at Impulse, who'll be talking first, and then I think Samantha Block and Stefan from Astrobotic will be speaking in a Q&A with Winta about, lunar mining to an extent, but mostly about propulsion and test. So that will be exciting as well. After that, we'll talk about recovery a little bit. It's not as big of a deal as it would be, at Spaceport or something like that, because, oh no, we respect. But the thing is, there's like 100 teams there, so that's a whole logistical problem. Here we can look out for you guys a little bit better, but there's still a procedure, so we'll talk about it. We'll have lunch. You guys will get tiny sandwiches. I'm so sorry, but the other ones were quite expensive. Unless you're gluten-free, in which case you get a slightly larger sandwich. You're welcome. They didn't have the gluten-free ones in smaller sizes. After that, we'll talk about podium presentations. Those of you who are doing podium presentations have gotten a link, gotten a schedule at 1 a.m. last night or 2 a.m. last night. That is the presentations. I've read through your abstracts. I'm very excited to hear about them. We'll be judging them on a little bit more subjectively because these are all different these are all vastly different systems. We're going to be talking about how you designed it, manufacturing or anything like that, challenges that you have faced. So be aware of that. We'll also have, I think, AGH, who isn't here. The Polish team will be calling in and doing a Zoom call of their podium presentation. So thanks, Poland. That makes us an international competition. We'll also be building some CERT rockets. I don't know if we have kits here. Peter has brought the kits. Thanks, Peter. He made them while driving in the car over here. 3D printers in cars. Didn't know it was a thing. But we have certification rockets. They're going to be hybrid rockets. You can get your L1 or L2 this weekend as well if you want to. If you do, sign up, but we have a little bit more of a limited supply. Peter's like, no. Not too many people sign up, but know that this is a thing we'll be doing for next year as well. But that's the thing. It's also fairly cheap. We can make it $100, including NAR certs. So think about it for next year. We tried to advertise, but I'm trying to figure out whether Discord's the best method or something else. Okay, what is far out? Peter, come. Peter made this, so he should say something. Hi, Peter. This is Peter Tarlay. He's from the University of Tennessee, but he's from Michigan. He doesn't want you to know that. Here.
Oh, is this the one that's working?
This is live stream. This is
Oh, wonderful. Hi, guys. For those who know me, I like to take on very large stakes, and sometimes I get all the way done with them. But where I come from, in Ann Arbor, there used to be a football coach who said, "Those who stay will be champions," and today, that's you. Some of these projects have lasted over a year, and those have been hard years, and some of you have crammed all that work into 1 year somehow and are still here. So to you, congratulations. But now comes the hard part. You're going to have to prove your worth. You're going to have to fly those projects that some parts might still be jerry-rigged, some parts, you wish you could go back and rebuild, but you did your best, and you're going to do your best. Your team leads and sub-team leads and those who worked under them have fought hard all year, and they are going to be in the most stressful positions of their lives so far, and we hope to make that easier on you. Watch them. Some of them have taken way too much caffeine to stay awake and get stuff done, which means they're going to dehydrate probably a lot faster than the rest of you. Make sure you force feed them water. Not actually, just make sure they actually drink water. Red Bull, while it contains mostly water, is not water. So there's that. We hope to make this competition something that is easygoing and allows you to show what you are capable of to an international audience, among your peers, and so that you can benefit from each other. But a rule book can only do so much. The rest of it is how you talk to each other, how you share ideas, and you try and make each other better for the next year. And so we hope to provide that venue for you. And we're going to have to be talking about a lot of safety stuff, but we hope you have fun. We hope you learn a lot, and that's why we all came out here this year. So, to this year and the years after, good luck. Hey.
Fuzzy. This is not a microphone that works for the people here. However, we're back. Turns out that maybe you can use this like microphone for exclusive content for the live stream. Just kidding. Okay. What is Far Out? You guys know it. You're here. You've bought into it. It's a hybrid liquid collegiate rocketry competition and conference, and we want to make it as such. I can't clip this. Started this year, and really, it's to design a rocket that can go as close to your stated contract apogee as possible. You know this. For those of you who don't, now you know. And really, why? We have a reason for starting this competition. We found that there was a gap that wasn't really filled by any existing competitions, where the logistics of hybrid and liquids are vastly different from those of solids. There's more care that has to be taken to them, and you really need somebody who knows these systems intricately. There's a lot of places things can go wrong, from your GSC to your rocket. Not that I want you guys to think about it right now, but you know the risks, and you want somebody who knows the risks as well, who's judging you. We have those folks here. FAR is amazing with liquids. We have the people who have been judging hybrids for years, building them and flying them, people who have actually flown them and not just looked them up. You know, we have folks who are here who can judge your systems, who've been looking at your systems from the start, asking questions, going, hey, you know, asking harder questions that maybe you don't want to hear about. But this is what we wanted to be doing for you guys. we want to make ourselves available to you to, you know, talk through anything. Please have an in-person mentor, but like the folks you have here are really happy to answer questions, happy, you know, to look over your stuff if you need somebody to look over it. So use these people. They're a resource for you during this competition, and they've been trying to be so as well throughout the year. We want to maintain an open line of communication as well. I'm going to skip a little bit, but really this is more chances to learn from other teams. We found that at other competitions, it was a little bit siloed. You wouldn't meet anybody until you actually came to the thing. You wouldn't be really able to talk to many other teams before you came to the thing. We want to foster that kind of stuff because the like more innovation is made, the faster, you know, like more innovation is made, the more you communicate. Otherwise, you're going to just be developing in your own ways, and you know, it's nice to have some outside opinions who haven't just been in an echo chamber the whole time. That's what we want to help with, and you know, hopefully we kind of achieved that in some sense this year through Discord, but we want to try to make that a little bit better. We're trying to have an objective scoring system for the whole thing. We found that otherwise, other like competitions, differences in first and second place would end up being based on something subjective rather than on the objective thing of how far, you know, the like efficiency of the motor. That's what we're looking at here. There's a complicated equation. Peter wrote it. It's there, but you will know what score you get, you know, if you can figure out the numbers that go into this. That's the nice part. Opportunities to use more materials. We are not EEE NAR associated. So you don't have to follow those kinds of things. This is one of those problems that, you know, led to the insurance debacle. But we want to basically allow you guys to innovate as much as, you know, your insurance allows. That's what we want. We want you guys to be able to build stuff. We want you to be able to launch stuff higher than 35,000 feet. You know, FAR has a waiver on weekends of 110,000, and the ability to do class 3 waivers. So think about it, you know, you have opportunities to grow here and not just stay in, you know, whatever, like you're like stay at 30,000, not go further. Also, we are very close to a lot of government centers and SoCal Aerospace, which has been already helpful in terms of finding sponsors. It's been great out here. You're near Edwards, you're near China Lake, you're near NASA Armstrong, you're near Air Farrell, blah, blah, blah. My tongue's tied. But these are all great places, and you should think about that. FAR. Speaking of FAR, we've got Mark here. Mark, do you want to say some words about hello? Pardon? You want to do more than hello? Come. This is Mark Holthouse. He's the treasurer of FAR, and he has helped significantly in running this event and helping logistics. You get this, you get this.
Thank you.
So, back when I got started in doing amateur rocketry, of course, what did I do? I jumped in right where no one else should do this. We built a liquid oxygen alcohol rocket that had 2,000 pounds of thrust for 60 seconds. That was an amateur record at the time. So from that, over time, we've been in different rocket organizations and found that they were usually fighting each other. So we formed the Friends of Amateur Rocketry, that's what FAR stands for. And it was basically to give a spot where people could bring their rocket and launch it. And, you know, you see EEE and NAR have these safety rules, or you see these requirements like I was looking at EEE, and one of the safety rules is no bipropellant liquid rockets. And it's like, why? And you know, I don't care if you come out the FAR with a rocket and you fail. It's a learning experience. And we don't have anything other than trying to keep the rocket safe while you're dealing with it and getting ready to launch. So that's why we have bunkers. The EEE and NAR, they all use this safety thing so that you're a long ways away, your rocket looks like this little thing on the pad, and you launch and it's like, oh, okay. We can be much closer because we have bunkers. We have concrete overhead, concrete on all sides and in front. So your rocket can blow up. And if it does blow up, it's not a bad thing. You learn from that because you won't blow the rocket up the next time. FAR has been in business now for 20 years. We started with just not even a cargo container. We had 10-acre plot of land, and we had a Lincoln log blockhouse that you could crouch down in and watch your rocket. And one of the first users of our site was Mythbusters. I don't know if you guys have all seen Mythbusters. Buster was one of their original characters in Mythbusters, and it was a crash test dummy. We blew Buster up twice. And so here we are in the Lincoln log blockhouse looking at Buster sitting on a throne that had 47 rocket motors on the bottom of it. And we had the Mythbusters filming crew behind us in polycarbonate cages so they wouldn't get hurt. And we watched Buster first time blow up in a cloud of fire, and then the second time we did it, Buster rose up about 3 feet off the ground. One of the rocket motors failed. It flipped upside down and jammed him into the ground. But so there we had our 4 original members of FAR, and there was basically nobody using our site. Now you come out, it's been 20 years. I think we've had just about every big engineering school in both California and the rest of the US come and use our site. And we have to push people away because our bunkers will only handle 200 people at one time. So I'm always continuously shuffling rocket teams around so I can get them to come to the site, but we aren't unsafe. So, and we've had a very good track record. You don't hear of anybody that has died or been injured out at the FAR rocket site. So we've been doing really good with that, and basically, and we've had lots of rockets blow up. And you can see pictures if you go and look on the internet. You see an explosion and pieces of rocket motors falling all over the place. That's an okay thing to do out at FAR. And actually, we were looking around the site yesterday, and we were finding pieces of propellant from solid rocket motors that have exploded out at FAR. And you can find propellant, sugar propellant, APCP, it's all over the ground out there. You can find it. We've blown up a lot of stuff, and it's okay because people learn from that. But 20 years, don't break my safety record, guys. So, so that's it. Thanks, guys.
All right. Lynn Johansson is the contracts manager at Mojave Air and Spaceport, which I think is far too boring of a name for the amount of stuff that she does here. She has helped out from so many angles, and I want her to talk a little bit more about Mojave Air and Spaceport here.
Good morning, everybody. Can you all hear me out there? Great. So, I've had a chance to talk to a few of you guys already, which I'm very excited about this whole event. So when FAR first reached out about wanting to hold the event here, our old CEO was here, and I was like, this is a great opportunity to get our tenants to know their future employees, which are all of you. And I am very thrilled that several of our tenants have stepped up, sponsored, are your speakers, are here and have generously donated all the free water that you guys are drinking. Hey, hats off to our Missions Linen and Galactic Company for providing all of the water for you guys so you don't, dehydrate out there, so drink up. Mojave Air and Spaceport is definitely a unique place to work at, be at, participate in any event that is held here. I always tell people that this is history in the making because you never know what you're going to see. You are always going to learn something new every day, and there are no 2 days the same. And there are not many places that you can work at or be a part of that you can say anything like that. I do hope that all of you guys go over to our administration building, meet some of the staff over there, walk through the halls. I call them our Hall of Fame because there are so many pictures of the first flights and first events that take place. And in reality, when somebody wants to do something new, they come here because we are the place that everybody wants to be. So I'm really happy that you can all be here and working with Jess and Far and the whole team of trying to get you guys organized and situated so that you can have a good event and an event that will be, this is the first of many. And you guys, again, are part of making history for the first event of this to be held here. So give yourself all a hand for wanting to put forth the effort and make this trip out here. I know that some of you have traveled a long ways to do it, and we appreciate that. And I hope that you all stop by and talk to our staff and our tenants and get your questions asked and answered of what it's really like to work in this industry on a full-time basis after you guys graduate. That's it. And Jess. There you go.
All right. Haha, that's the last slide of the template. So, competitors, Mars, Jupiter, and Saturn. I didn't change it. Oops. But we're going to start talking about safety in just a second here. I don't think this will be streamed, so let's keep that in mind. But let's jump over to that. Thank you all for coming, and I hope you have a really good time. I hope that you're not too stressed. Get some sleep, drink some water, and let's launch some rockets. So yeah, thank you. Okay.
glad to be here today and talk about what our mission is and what we're doing. I guess the kind of where Impulse space, the origin story of Impulse is very much tied to SpaceX. I have a video. I'm probably just going to go over this a little bit quickly today, but our founder, Tom Mueller, was the first engineer, first employee at SpaceX back in the day. So really one of the founders of the new space movement. I joined in 2005, worked with Tom for nearly 16 years, and talk a little bit about the accomplishments that SpaceX made that really enabled companies like Impulse and other companies to be around. Pretty much innate in our company is that same sort of development ethos and hardware and fail, fix, fast type of approach. So I'm starting here with like the SpaceX origin story because it took 10, 15 years from 2002 to this recent inflection point of mass to LEO. So when I started in aerospace, people weren't launching once a week, they're barely launching once a month. 3 launches a week is kind of the norm now. So obviously there's been this inflection point that everybody's seen in taking a lot of mass to low Earth orbit. Launches nearly every day, multiple companies, reusability is here, Starship is here. They just had a very successful launch. So you can see the curve is going to keep going up on this, which is great for everybody in this room. That means more rockets, more opportunities to go work here, right? MEO and GEO orbits have not seen that yet. We believe at Impulse it's just a matter of time. We believe we have good solutions to transfer some of this mass delivered to low Earth orbit to those higher energy orbits. So we are an in-space transportation company. We don't do launch vehicles. We work with launch vehicle providers to make sure our system fits within their payload fairing, within their lift capabilities, and we work to deliver payloads or execute missions in the solar system off those launch vehicles. And I'm going to talk to you about Helios and Mira, 2 of our vehicles that we are in development. One is on orbit now, but you see where we were the last 10 years from this plot. So basically Impulse picks up where SpaceX drops off. Our goal is to massively reduce the cost of access to any orbit. So whereas accessibility is here today, affordability to low Earth orbit is there today, we want to do the same thing for any missions in LEO, getting to GEO, going to lunar, as I said, pretty much anywhere in the solar system. I'm going to play a short little video here for our Helios system. So what you're going to see here is kind of the end of the launch vehicle phase, dropping off the Helios stage, and you'll see kind of the conceptual execution of our mission. There is no audio with this, so you're not missing anything. But it shows conceptually what the Helios vehicle that we're in development now will do. So riding along within the payload fairing encapsulated in there. So we all are totally within a launch vehicle. We separate from the upper stage of the launch vehicle. We turn on our Deneb engine. That's a 15,000 pound Oxbridge stage combustion engine. What you're looking at is a stage about 10 foot in diameter, 10 foot tall, with double that in the payload volume that we deliver. So could take multiple payloads, drop off a large, maybe primary payload, drop off some of our Mira spacecraft that we are flying now, and really can package together this capability that extends LEO mass delivery into GEO. Performance capabilities, about 4 tons to GEO, 6 tons to lunar, TLI, and about 4.5 tons to Earth escape, going places like Mars. So those are the capabilities that we provide. Why is it important, or what's our mission profile, is sort of this map of what a Helios mission will look like. We will go to orbit on T0. We get launched on a launch vehicle. 10 minutes in, we are in orbit. About 2 hours later, we're by that time we're separated from the launch vehicle. We're prepped and ready to make our first burn. So we condition the engine in. We look much like you see on the right there. We've just got the payload on top of our fully loaded stage. And within about 2 hours, we're going to begin our transfer orbit to GEO. So make our first burn, maybe 6 to 8 minute burn. We transfer up for under 6 hours to get to the top of the GEO orbit. We perform a burn where we circularize and drop off the payload. And there you go, you're a 4-ton satellite and you're in GEO. Within 8 hours, you can turn around and fly the next day another GEO mission if you want, because there's a reusable launch vehicle waiting for you. That is our mission, and that's how we're going to leverage our system to take that mass that arrives in low Earth orbit and deliver it quickly to geosynchronous orbit. So we can have customers up there within an 8-hour period. Some of the electric propulsion systems are going to take months to get there, and that's really the value that we provide, along with really a high cadence. We want to be on the same cadence of these other launch vehicles, so we want to be making a lot of these stages so we can support that massive increase of the GEO mass delivery. After we execute the mission, drop off payload, we'll, you're really far up there, you got to get out of that orbit, so we'll perform a disposal burn to stay in kind of what's called a graveyard orbit, and just park our vehicle up there. So the development, we've started design in the last 6 to 8 months. We've been into the design phase. We're putting together a lot of hardware right now in our Redondo Beach facility. So we're really thick into the development of the Deneb engine. Some pictures that we're showing here of the Deneb hardware. Basically, the top right is kind of a early phase model of what that stack looks like. It's a regeneratively cooled, ox-rich stage combustion engine, radiatively cooled nozzle, and then at the top right is some of the hardware we have in work now. That is our first thrust chamber, copper-lined Inconel jacket closeout, kind of a traditional thrust chamber that we're putting together now in Redondo Beach that we are going to be testing very soon. So if you're, as you guys know, if you're upper stage, you got to be very mass efficient and very high performance, because really hurts to get all that mass up there. So our design is intended to be the highest performance LOX hydrocarbon engine. We do that with liquid oxygen and methane, 2 cryogenic propellants, running a large area expansion ratio, running an ox-rich stage combustion cycle. And then I think we got a really great team to do this. We bring a lot of people from that world of the most reliable engine. The Merlin rocket engine flies pretty much every day, 10 engines a day. So we bring a lot of engineering and technician experience over from that, as well as a lot of great team members from some of the stage combustion engines like Raptor that have been in development. We're also building a test site up here at the spaceport. So really excited to move in there and start testing this engine. We should be testing in the next month, testing our power pack. So we have basically the turbo pump, and some of the parts you see at the bottom row are going into that turbo pump. We have our igniter at the left. That's a GOX methane igniter, turbine rotor, pre-burner, and some of the housings. So we do all of the additive development and all of the printing in our Redondo Beach facility, machining there, so we can iterate on parts very quickly. So yeah, the next year we'll be into development on this engine out here in Mojave. So that's Helios. That's the future, like the next year to two of our company, which we're really excited about. I think that's really in the wheelhouse of what our team is set up to do. I think Mira is another product that is also really suited to our team. Talked a lot about the propulsion capabilities that we have, but Mira is a full-fledged spacecraft. We launched our first Mira in November of last year. So it's been on orbit for about 6 months. I have kind of a summary of what it's done so far in a later slide, but this was brought together all facets of a spacecraft company, avionics, flight software, structures, GNC. We can do all of this in-house and really demonstrated with this vehicle what we're capable of doing. Again, this is a spacecraft that rides in a transporter mission that you guys might be familiar with, where ride share of multiple satellites could go on a Falcon 9 and get dropped off. So our spacecraft that we built has about 600 meters per second of payload capability at 300 kilograms. We use 8 of these safe thrusters. So if you can see in the image, there's plumes coming out of the spacecraft. And in the bottom right, you can kind of see some of the bell nozzles of the safe. So we actually use a nitrous oxide ethane system, which is a little bit novel for this type of mission. There are a couple others that chose these propellants. We like these propellants because they're storable, non-toxic, and fairly easy to use. So that's pretty much the backbone of this system. Have a video, don't have great audio here, but wanted to share this of our safe thruster in action. So you see pre-test. This thruster basically fits in the palm of my hands. We test this thruster in our vacuum chamber in Redondo Beach. This is a 5-pound thruster, so you can see it is started up in vacuum and the radiatively cooled nozzle. So you can see as we fire the thruster, heats up, we are firing into a diffuser and pumping out the exhaust gas. We've run this thing for about 30 minutes at a time, so it can run a 30-minute burn for these higher energy orbit transfers. We can also pulse the thruster. We use these thrusters to steer the spacecraft once we're on orbit. But yeah, this is also kind of a unique capability we have where we can test these small thrusters in a vacuum chamber. And again, this is an Impulse. We pride ourselves and really emphasize doing the vertically integrated everything in-house. So this thruster has a couple solenoid valves on it that we build in-house, a spark igniter. We print the thrusters themselves and test them and assemble them. So that first mission is on orbit. We're up there 6, maybe pushing 7 months now. The team that built it, probably like 40 to 50 people. We went from a clean sheet design to being on orbit successfully in about 15 months. Yeah, really, as far as projects I've been involved with, and I've been involved with some of the Falcon, the Merlin, Starship projects, this was definitely one of the most kind of fun and focused projects I've got a chance to work with. But clean sheet design, about 15 months. We think we performed one of the largest orbital maneuvers for an OTV on the first mission, about 100-kilometer altitude raise. So some of the objectives are listed there. I have a video. If you can catch it, you're going to see the CubeSat that we deployed. So this is actually a video from orbit from a few months ago. I hope you can see the payload popping out here. There you go. And in the bottom right, you can see about 4 of our 8 thrusters firing on the Mira spacecraft. They're glowing in shadow of the Earth. So our primary products are going to be the Helios stage at left, and the Mira can ride along. We can put multiple Miras on a Helios, on a GEO sort of geo rideshare mission. I think I have a video here kind of showing some of the capabilities of that. So again, we have plans for an adapter ring. We can drop off Miras. We can drop off other spacecraft. The Mira revision that we're working on now has the fully deployable and actuated solar arrays. Again, we have that safe propulsion system, the same system we're flying now. So we'll have orbit change and delta V capability. Obviously, dropping off other satellites, so we can go amongst different orbital inclinations and drop off satellites progressively. Those assets can go do other things, and that's kind of a service that doesn't really exist for GEO right now. That's enabled by our Helios stage and Mira spacecraft. So things that people want to do is obviously observation in orbit, propellant depots. Want to put propellant on station so it's available for other spacecraft. We actually have one mission looking at sort of a demonstration of that. But yeah, there's a lot of opportunities, a lot of things that we hope that Helios and Mira will enable. I mentioned vertically integration. So again, we pride ourselves on doing everything in-house in our Redondo Beach facility. That's printing, that's machining, just touching on some of the avionics components that we build in-house, star trackers, engine controllers, and sparkers, sensors, valves, igniters, solenoid valves make in-house. We wrap overwrapped, composite overwrapped pressure vessels in-house on a winder. We do all the testing, and then obviously go to the launch site and integrate it with the spacecraft. With that is the lower right picture. Full service partner, so if you guys want to launch with us, we offer mission design, launch procurement, figure out insurance, and then operationals. We have operations teams, so we have a spacecraft on orbit now. There's people that are interacting with that daily, checking health, getting data down, and making maneuvers as we need to. And then a little bit of the background of the company. So we started in 2021. We're just about 3 years into it. Post Series A, we got about $70 million of funding, 110 people and growing. We have a 60,000 square facility in Redondo Beach, and just more recently we have a test site 1 out here in Mojave that we're developing to do some of the propulsion system testing on. And so far 3 vehicles, one in orbit, Mira is in orbit, Helios we're working on now, and then we have designs for a mission of a Mars lander. And with that, that's hopefully you know more about Impulse Space and what we're doing. Does anybody have any questions? Go for it. Yeah. Yeah, the question was about reusability and the plans for do that in space. That's not currently our focus. Obviously, you'd be pretty naive to think that's not going to happen at some point in time, obviously. So we want to enable a system that can go do the first step and get from LEO to GEO efficiently, but you can imagine that in the future that will be highly desirable in terms of reusing some of this. And that's where things like propellant depots obviously would play into that. Yep.
What are some major lessons that you learned from on orbit with Mira that you'll take forward with the future Miras and Helios?
Okay, yeah, the question was major lessons learned on orbit and what we'll take forward with us. Yeah, I think it's lessons that we learned is I think communications can be difficult at times. So I think that was kind of one of our lessons learned of just working through some of the communications issues. I think I was actually pretty pleased at how much of the development objectives we could get to. So we did have contingencies we could go. We ideally wanted to do thing A. We got to do thing B. Got to do more in that realm. But I think the communications, I think, was the thing that we learned the most about on the first mission. Owen? Good question. That was a good question. Good question is how important is Starship to this? I think that's going to be extremely enabling and huge for us. I don't think it is required for what we're trying to do. I think you saw the inflection point of what is already being delivered today on orbit. We all know there's emerging launch vehicles that are right behind that. It's going to make that even more possible. But Starship is a game changer across the board. So we love it. It's going to be really good for what our system is designed to do. It's designed with that in mind. But I think it'll probably just knock it up another notch in terms of what we'll be able to do. Yep. Yes. Why went nitrous ethane? Yeah. Question was why did we go with nitrous ethane? And really, it's just the reusability aspect. Sorry, reusability. The serviceability aspect of it. So it's non-toxic, storable, non-cryogenic. Yes, it's a little bit lower in performance. I think we've gotten pretty good performance out of the chemical combination. But really, for those reasons, we wanted Mira to be very accessible, storable, something that you could just basically pull off the shelf and go fly a mission. Yep. Sizing, yeah. Question was about the sizing of Helios and if it's a one-size-fits-all. Yeah, so we've surveyed all of the launch vehicles and really are designing to a point that is one-size-fits-all.
What would it cost to deploy, say, a triple CubeSat?
Sorry, say again?
Deploy a triple CubeSat? What kind of range of cost are we talking?
Oh. I'm gonna defer to my business development team on that one, but it is accessible. I mean, we fly missions with a lot of capability in terms of CubeSat deployers. So and we're definitely interested in that. That's what we want to enable. We want to be the provider that can launch the big satellites, the small satellites, just service the full gamut. Yep.
Are there concerns about boil-off cryogenic propellants of methane and liquid oxygen in Helios? And how did you make that trade between going forward with those propellants and maybe losing some capability for longer missions?
Yeah. The question was about boil-off and the propellants that we chose for Helios. Yeah, to the LOX methane system, there's fundamentally, we picked those propellants. They're high performance. There's definitely a trend in a lot of the launch service providers going to that. Obviously, Starship is LOX methane too, so there's a lot of synergy there. Boil off will be a problem for anybody who wants to do a long mission on orbit. So that is definitely a technical challenge for us and anybody to do it. But the missions I showed, kind of the baseline missions, are all executed in 8 hours. So that's still really well suited for these propellants. Yes?
How's work-life balance? Work-life balance.
How's work-life balance? That is a good question. I think when you're in a startup environment, there's always that enthusiasm to get the job done and to work hard towards a goal. I think our team has struck a pretty good work-life balance. I think that's kind of emblematic of the people we hired, people who want that sort of work-life balance. Yeah, it's great working with a team that's ready to go after a goal and work towards it, but also a team that has other interests out of work that you can talk about at the office. So I think we've struck a pretty good balance at Impulse. Okay. Yeah, the question about the Relativity and Mars missions. Yeah, so we are on contract to do the Mars mission with Relativity. I think I would say right now the priorities for our company and Relativity, that's a mission we do want to do. We're focused on the steps to get there. They're focusing really hard on the Terran development, and then we're focusing on basically the same technologies for what we've offered for that mission. So Mira is core. The systems, spacecraft systems and propulsion is core to that. So it's all kind of on our same roadmap to get there. All right. Thanks, everybody.
Give us just a couple minutes to reset here, and then we'll add some chairs to the stage, and we'll start our next speakers.
Thank you.
It's not possible. But we'll get started now, I suppose? Or do you still have the, okay. There's no other one. Oh, yeah. Okay, so we're gonna have a little bit of a Q&A chat, a talk with Samantha Block and Stefan Lamb of Astrobotic. So this will be moderated by Winta Ghebreyesus, and she is, let me give you a whole spiel. She is a versatile character. Winta is the founder and COO of Moontrades and a PhD candidate in aerospace engineering. Winta is a leader in aerospace innovation and sustainability. At Moontrades, she is at the forefront of developing AI-driven lunar mining technologies with a focus on sustainable resource utilization and global STEM education. Her efforts in creating advanced robotic tools for Earth and lunar applications are a testament to her commitment to sustainable exploration and technological progress. And Winta is a director at Space Place Planetarium Canada and an executive team member at Women in Aerospace Canada. Also give you a little bit of a spiel about Sam and Stefan beforehand. Samantha Block has served in multiple active duty and civilian roles in the Air Force for 20 years, including as a negotiator, an acquisition program manager, a helicopter flight test manager, and a live fire test and evaluation manager. Her work with the Air Force included assignments with Special Operations Command, Air Force Test Center, and Air Force Test Pilot School. Now with Astrobotic, Samantha wears multiple hats, including as a systems engineer on the, oh goodness, SOGDOR VTDL program, a program manager on the test team for the Griffin lunar lander, and as a range safety officer for Astrobotic's test site at Mojave. Stefan Lamb works as a senior test engineer and payload manager at Astrobotic and launch conductor for flight tests of its Zodiac rocket vehicle. Prior to joining Astrobotic in 2022, Mr. Lamb worked as an aerospace engineer for Masten Space Systems from 2018 to 2022, and an engineering technician for Kaufman and Robinson from 2017 to 2018. So give them a round of applause.
All right, good morning, everyone. I'm delighted to welcome Samantha Block and Stefan Lamb from Astrobotic to our session today. A little bit about Astrobotic. It was founded in 2007, and it has been at the forefront of advanced space robotics technology for lunar and planetary missions. Headquartered in Pittsburgh, Pennsylvania, the company has grown to well over 200 employees and has achieved numerous milestones, including their recent Peregrine lunar lander launch. Astrobotic's propulsion and test team is currently located here at Mojave Air and Space, and we're over the moon today to have Samantha and Stefan joining us to share their insights and experiences. So let's give them a round of applause. So let's kick things off with getting to know a little bit more about each of your journeys to Astrobotic.
Hello, I'm Stefan Lamb. I'm really loud, so this is probably going to come through clear for you guys, which is nice. I have that problem at work too, so you can ask Samantha about it. So prior to Astrobotic, I worked for Masten, which was acquired from Astrobotic, and so I was there since 2018, and I kind of worked my way up. I actually started as an intern in the group, and it was my first experience into a rocket company. Before that, I worked at a plasma physics lab, and because I'm a physicist from college, so I kind of have a not direct route from aerospace. So going from physics into rocketry. So I'm kind of a propulsion expert now by osmosis, not by education, but working in a place and being able to ask good questions, you'll learn a lot with a lot of very smart people that are smarter than you. So do the best you can to surround yourself with very smart people. So now I'm more integrated directly into the Zodiac test cell that I kind of run the show on Zodiac. I'm the launch coordinator for that. That's our 1,200-pound class isopropyl alcohol and liquid oxygen VTVL rocket. That's a lot of words in one, but basically we fly payloads for flight opportunities, or actually SDSU. We're going to fly one for that team. We've done a bunch for University of Central Florida, for JPL. Pretty much anyone who wants to fly on. All universities can fly payloads on there as well through the Flight Opportunities Program. So it's something to look into. Universities have a good budget doing that too, so it's something worth looking into.
Thanks, Stefan. Good morning, everybody. So my name is Samantha. Like she said, I do want to warn you guys before we start. I am hearing impaired, but thanks to military service. This is acquired hearing loss. If I don't understand any questions coming from the audience, please bear with me. I'll do my best to turn my hearing aids up and hear you guys. I attended Michigan Technological University up in the Upper Peninsula of Michigan, graduated from there in 2003. I went through their ROTC program with the Air Force. So the day that I graduated, I also commissioned as an officer into the Air Force. And for the next 20 years, I worked for the Air Force, both in an active duty role and then in some civilian roles as well. My career took me on this roundabout loop. For those of you who are familiar with the military, they choose your jobs for you and they tell you what you're going to do, regardless almost of what your degree was or what your wishes are. So I wore multiple hats in the Air Force, initially starting as a negotiator. I was trained in everything from contract negotiation to hostage negotiation. I went through training with the National Security Agency as a brand new 22-year-old straight out of college, so that there was some excitement there. Got some great opportunities to go downrange to some places that we don't talk about and do some things that we don't talk about. After that, I got into acquisition program management and then had a wonderful career broadening opportunity in flight test and decided to jump on that, and I really found my niche. And so I spent the last half of my career with the Air Force as a helicopter flight test subject matter expert. And so our job was to design, build, and test new developmental helicopters with new new subsystems on board. So I was actually the first flight lead on the HH-60W, the new Hawk variant helicopter. It's called the Jolly Green 2. I took that aircraft from a paper design to its first flight. And then shortly after that, same thing with the MH-139A, the Grey Wolf, which is the Huey replacement. So the old UH-1N helicopters finally retired, and the Hueys now, or I'm sorry, the Grey Wolf's now taking their place. I was also the first flight lead on that aircraft too, so took that aircraft to its first flight as well. Along the way, I picked up some expertise in live fire tests, so anything that blows up or can injure my helicopter or the people on board are things that I was able to specialize in both the test and evaluation of that, and then the redesign for vulnerability protection on the aircraft itself. Came out here to Edwards, was fortunate enough to attend some training at Test Pilot School, Air Force Test Pilot School on Edwards, and then was fortunate enough to be asked to teach for them. And so I taught their short course. So if anybody is interested in what the Air Force Test Pilot School short course looks like, National Test Pilot School here in Mojave has one as well. A very similar kind of setup for how that class works, and you do not have to be a pilot to go through the short course at Test Pilot School. Despite the name of the program, you do not have to be a pilot. So there's some wonderful things to be learned going through that program. After that, I worked some classified programs that we won't talk about. Finally, 20 years were up, and it was time for me to move on. So I joined Astrobotic last year, wear multiple hats here. Most of the time, I'm a program manager, making sure that all of our projects are staying on cost and budget, schedule, and meeting our performance objectives, wrangling the herd of engineers to make sure that they get the job done. On test days, I am a range safety officer for some of the flights. The only one I'm not range safety for is actually Stefan's, so I don't range safety for Zodiac, but I do for others. And then I wear a part-time systems engineering hat when we need that on the Zogdor program. So multiple hatted out here, which is the wonderful benefit of having a small team. You get that opportunity to dip your toes in the waters and really test out different roles and responsibilities.
It's always nice to hear, everyone's different journeys to where they are now, and I think both of yours are really inspiring, so thank you for sharing that. And I did see the Test Pilot School actually on the way in this morning, so that's really neat. I'd love to get my PPL one day, but I know that's a little different in terms of what they're offering here, right? But maybe I'll start with you, Samantha. Can you shed some light on what the team does here for the propulsion and test team at Astrobotic, especially in the context of delivering the Zodiac vehicle? And well, I guess that's kind of your work too. but how does the environment here really support the students and also the interns and the employees here?
Yeah, sure. So I was speaking to, I've already forgotten your name. Is it Beth, maybe? Bella. I was close. I was speaking to Bella actually just a little bit ago about the interns. So a wonderful thing for a program, or a company, I'm sorry, and a team specifically as small as Astrobotics is when our interns come here, they are out on the range on our ground crew nearly from week one. We will get them the training they need to be safe, and then they get to shadow right away. And if they show the right knowledge, the right motivation, the right passion, and the right level of safety awareness, then they can step up into a ground crew role during their internship. If you would go and intern for some of the larger companies, or even perhaps for the DoD, it is likely that you'll spend a good bit of your intern program filling coffee, printing things, running copies, you know, sitting in meetings, taking notes, those kinds of things. Sadly, I saw far too many Air Force interns that did exactly that. I even saw far too many Air Force lieutenants that did exactly that. So it's very exciting to me to come here to Astrobotic and see that our interns are on the ground running from day one, given true responsibilities to do real work, and getting to see the fruits of their work by the end of their intern program, so they can take a small project from beginning to end during that internship. And that's a wonderful opportunity for every college student, something I never had, and I really wish that I would have had.
Same. Yeah, sure. Yeah, that's pretty much one of the best things at Astrobotic, and even before in Maston. We've maintained a lot of that similar culture that we had there before, where it's always a small team, which you guys are all part of, right? It's a natural fit. It's an eclectic group of everybody from different backgrounds, which is great, and it really builds to the best team. And one of the best things we've always done is given exceptional intern opportunities, working on real things. You'll make real things. For instance, right now we're integrating a payload for a customer, and we're going to fly in 2 weeks for a student payload program. And one of the interns that was working with me directly, he helped, you know, and I give him a design, but a lot of it we give hands off as much as we can. So I'm going to give you the general idea, and then I'm going to let you work with it and then give you guidance along the way, right? He designed the whole power distribution box for all these 16 different 2U payloads for an actual payload that's going to fly. And that was his project. He owned it. I would give him insight and everything when he needs it. And that's really representative of the whole process that we give everybody. We don't make people be on ground crew if you don't want to be, obviously. But most people want to be, so you get hands on the rocket, you get to be there during a rocket test, you get to see it, you get to learn a lot. And I think that's one of the best things that we've always offered, and that's pretty critical, I think, for a lot of people as a big step in their direction to kind of get hands on the ground and get to integrate into ways that they didn't get to before.
Absolutely, and I think a lot of schools are also noticing the need for experiential learning and as much of that hands-on experience as you were talking about. Could you tell us now a little bit about the differences between Zogdor and Zodiac? Sure.
Yeah, Samantha's a lot more integrated into Zogdor, but I can speak to a little bit and she could probably add to it. But so what Zodiac is, it's a fully autonomous vertical takeoff, vertical landing rocket. So it has its own brain. It doesn't have any landing system detection, so no LiDAR or anything like that, but what it's using is an IMU, a GPS, and then a very well thought through software program, right, that flies itself. So we use a trajectory development tool and all of our in-house own development tools for that. And we can fly whatever trajectory that most people want. So we have a wide variety of trajectories that people ask for. A lot of them are simulating kind of like a lunar landing, right? How they come in at an angle. So we can give them that simulated lunar landing from a short altitude though. So we really optimize for the flight for our vehicle. It's 500 meters or below is standard. So what Zogdor is doing is filling that next gap from low suborbital to still suborbital, but in that next range. So it's higher, faster. It's got a fairing, right? It's much higher. It could do supersonic, which is something that Zodiac, if you've seen a picture of, it's an open frame, right? It's not aerodynamic. It's got a maximum of about 27 meters per second. Total vector is that it can go, so it's fairly low. It's representative of a landing at the very last part of a lunar landing or a Mars landing, but Zogdor is that next step to provide the similar service in testing payloads, but in a much higher altitude, higher performance, that next supersonic segment that a lot of people are shooting for.
Yeah, so one of the great things about both of these vehicles is Zodiac has full flight certification, and so you can bring a payload, put it on Zodiac, and test your payload on a fully certified, qualified launch vehicle, including everything that the FAA needs for us to meet our licensure requirements and fly this safely. Zogdor will be there in the future. We're not there yet. We're still in some of the development phase of it, but that way we can take experimental payloads, put them onto a certified, qualified rocket, launch it up, and do all of the testing that any customer needs. So although the majority of our customers, as you might expect, are more in the NASA realm, or even some of our competitors, we will also very happily bring on student payloads. We have some student payloads that are actually flying next week on Zodiac that Stefan can talk to. Some of those are from only 6th graders. So these are very young teams that are bringing technology to us, bringing ideas, and if it doesn't work, that's okay, but we have sparked a scientific interest in the minds of somebody very young and set them up for this attitude of, I can do this, I can take an idea, I can put in the work, I can see what that does and how it works, and then grow that interest as they go. And so Zogdor, super exciting opportunities there to just go higher, faster, farther, and test more payloads then, a little bit more complicated payloads, heavier payloads, and maybe eventually some point-to-point payload deliveries as well.
I'll give you the NASA answer too. What we really provide is payloads have a technology readiness level called TRL. You guys might have heard of this, right? So when you design something, it has a TRL level. There's kind of a sinkhole from TRL 4 to TRL 6 to be able to get on a real mission. What we provide is kind of a leapfrog to go from 4 to 6. So we have a relevant environment, a rocket-powered lander that they can fly on, and their payload flies, and usually it's in TRL 4, right? And then by the end of the time they're flying, they're TRL 6 or TRL 7. So that's really kind of the quick answer of what we provide for most payloads. They're wanting to go on a scientific mission or on anything like that, but you have to go through that very specific technology readiness level, and we provide that step in the way. And so Zogdor will do the same thing, but for different classification of payloads. So that's really kind of the crux of it if you really get down to it quickly.
Yeah, I'm glad you mentioned TRL levels. Our startup is TRL 2 right now. We're still going through the early stages of prototyping our lunar rover. Oh, yeah. So it is really exciting.
We'll come fly. No,
yeah, I wish. Okay, so in terms of communication and the importance of teams and integration in the different subsystems that you're working on, can you talk a little bit about the importance of partnering with organizations like ULA and NASA?
Yeah, you want to be friends with NASA. That's the answer to that question. That's a short answer to that question. United Launch Association and NASA, NASA has done a really good job. If you guys are familiar with the CLPS program, right, the Commercial Lunar Payload Services, that's really where a lot of the lunar action is going on. Our previous Peregrine mission was part of that, right? What NASA realized, they realized that they're kind of chokeholded by their own bureaucracy and the speed at which they can do things. So they're looking to industry. I mean, SpaceX has been a great provider for that, right? And Impulse will be doing the same thing, I'm sure. It's partnering with industry so we can do things faster than they possibly can. And they realize that, and so they want to be part of that because we have to compete with a lot of other countries that are moving fast, right? So the big thing with NASA is developing those. NASA has a lot of technology that they've helped fund that you have access to if you're friends with them, so to speak, that you wouldn't have access to otherwise, right? A lot of ITAR information, a lot of interesting material stuff. That's where all GRCOP and all that stuff came from, right? All that's funded through most of NASA programs to some degree, either through Science Technology Mission Directorate, STMD, or Science Mission Directorate, right? That's really the two wings of NASA that you guys in any industry for aerospace, you guys will be part of to some degree or another. So developing that relationship, and it's something that Mastin had developed a long time with the flight opportunities. We really helped pave the way for a lot of the current payload flight providers on how NASA was going to fund and pay a commercial company to provide a service like that. So we actually helped define and set up a lot of that original architecture, and it's shifted over the years, even since I've been there, on how it's been. But so we have a lot of good contacts in NASA through that opportunity, and it's been really, I mean, having good contacts there, it can't be overstated, that's for sure.
I want to say too, this doesn't always make me friends among my coworkers or my bosses, but I firmly believe this. Your regulating authorities should be your friends. That includes things like OSHA, Environmental Protection Agency, the EPA. If you look at those as hurdles that you want to, that are bothering you, you want to hide things from, you're probably approaching this wrong. So your regulating authorities, building a positive relationship with them, understanding the hows, the whys behind their requirements are going to help you do your job better. If you are constantly gnashing teeth with them or trying to avoid them, it will come back to bite you. You might feel like you're moving faster at first. You might feel like you're saving money at first. In the end, it will hurt. So you might as well start at the beginning with some good friendships with them. I have never found my regulating authorities to be my enemies. They have my interests at heart despite what it feels in the moment. So I feel like that's really important to foot stomp here. I know that testing out here in the desert, you guys here had to worry about some environmental protection rules and regulations to overcome to come out here and test your rockets. You might occasionally say something ridiculous about the desert tortoises. Why are we having to do this about a stupid tortoise? Trust me, it matters. And if you piss them off, you will not fly. So, you know, don't build that kind of a relationship. Instead, look at them as your friends, look at them as your help. They have resources, they have information that can be helpful. NASA and ULA, 100% your friends. Build those relationships. My phone a friend Rolex, after being in the aerospace industry for 21 years now, my phone a friend Rolex is very broad. And that's only going to benefit me and benefit my projects and benefit my company as a whole.
Well said. No comment on that. I think it's true. I guess from acquiring Mastin, how has that kind of shaped the future of the work at Astrobotic and the integration of some of your new systems?
Yeah, Astrobotic has been a fantastic company to be acquired for. I know in the transition, I'm one of the few Mastinites that are left from the original team. And you know, there was a few things that with John Thornton sitting down when he was acquiring, and we all met before some of us decided to stay. You know, they've been really good in supporting us in kind of maintaining the culture that we have, because it's a little different right here when you're small and you're out in the desert, and it's a high competency team where everybody kind of does everything and wears a lot of hats. You move differently, right, than a more well-structured. There's good and bad to that, right? Like you're often having to do more than the average person, so it requires a certain type of aptitude, and so you know there's kind of a blend to that, and Astrobotic's been fantastic with that. There's a lot going on right now to try to integrate more of the two, right, so we don't feel separated, and that's a hard thing to do, to cross-pollinate between two things, but there's a lot of programs that both we're working on right now, and then with long-term view of how we're going to best support the total kind of view and dream of what the company wants to be, right? And so that's been a good. I think we provide a wing to what they need to fill a gap that they need, and then they're the same to us, right? So it has been really mutually beneficial. I'm happy that we did get purchased by Astrobotic for sure to see it. So.
Yeah, so I was not with Mastin. I joined the company after the acquisition. But as you guys are looking post-graduation and trying to figure out what do you want to do with your life and where do you want to work, like Stefan said, there's pros and cons of small businesses versus larger corporations. And it just comes down to where do you feel like your skills and talents will be the most respected, the most used? Where do you feel you can learn the most? And what are your goals eventually in your career? If you're looking for stability right off the bat, then probably a small business is going to be a little bit higher risk for you. But if you're looking for a little bit more autonomy on a team, opportunities to do things hands-on, go out and make some mistakes, then maybe a small business is exactly the place that you want to go. I have now done both. You know, working for the DoD conglomerate, being as large as it is, I lived in the land of administrivia and the land of processes and protocols, and the land where building a building takes 10 years just because Congress manages our funding, right? So that's frustrating. At the same time, though, I have learned comfort in processes, comfort in protocols, comfort in the chain of command, and so that was the basis of my career for such a long time. So coming now down to a small company like Astrobotic, we have the access to the resources of headquarters, but yet we're a very small team here, geographically separated in the middle of the desert, getting a chance to do hands-on things. So having that reach back to headquarters for the resources that we need and the support that we need and the funding that we need is helpful. And having the autonomy to actually hands-on test things is also helpful. I don't think you're going to find very many program managers at headquarters Astrobotic that get hands-on test days like I do. And so that's one huge benefit for me specifically of being out here on this smaller team, is I get to do both.
Awesome. And I totally get it in terms of the red tape, especially with the kinds of activities that we like to do. And for the audience here, which is a lot of amateur rocketeers and enthusiasts, what are ways in which they can engage in some of their projects, potentially with Astrobotic?
That's a good question. I mean, we've supported, one thing we definitely always support is if people want to come do a tour at our place, I'll walk you and show you the flight vehicle. You can ask me questions about it and we can talk through it, which is always fun. So that's an easy, low-level thing, right? Support is always a challenging thing. It's going to be, timing is critical, right? I've supported more than one rocket team or robotics team or things like that for college teams or high schools, things like that. You can reach out through LinkedIn and you can just ask, right? So the worst somebody's going to tell you is no, right? So I would always ask, and so I'd say reach out and ask. That's the first thing. And sometimes we might have enough time, but it's always going to vary, right? Any full-time company and anybody knows, like it especially goes in wave with testing environments, right? Where you're testing and it's busy and you're working many hours a week, and then it hopefully comes down a little bit so you have a little break. But if you can sneak in one of those times or in one of those relative times, but most of the time if you reach out and you're asking and you have a specific question, I would say, if you have a specific question and you can verbalize it, like this is the key to learning, right? The best thing about learning is knowing to ask the right questions. So in the same way, if you have something important and you can ask someone a meaningful and pointed question that you can get something for them, that's going to be the easiest way. But as far as full support, trying to build relationships, internships are a good way to do that. Or just, like I said, reach out and ask.
Yeah, LinkedIn is a really good place for you to start building your professional networking. I'm in no way sponsoring LinkedIn, but get out there, like a couple companies, follow their activities, see who you see active on there, pay attention to the news, set your Google alerts. And as you learn what's going on in the industry that you clearly have a hobby interest in and you're interested in following that up with career opportunities, that's how you start building those connections. And then you start sending emails, start making phone calls, visit some companies. Stefan and I are kind of identified tour guides here at Astrobotic. We just hosted a tour this morning. That's why we came in here hot and sweaty. We were out at the test range early this morning with a group from NASA. But 2 weeks ago, I had a same-day tour, also from a group with NASA. They just kind of showed up. They called with about 45 minutes notice, left Edwards Air Force Base, drove out here, and our business development person looked around the office and said, Samantha, you take them. So we can do the same thing for college groups. We can do the same thing for students that are looking for exposures and opportunities. Of course, there's some rules and things that we have to work through, but that is absolutely opportunities that are out here.
Yeah, I wanted to add to that. So because of the flight opportunities, you want to look out for those flight opportunities payload options. They happen every year. Like for SDSU, if you guys know your Professor Ping, because he's working on coming out, he probably needs some help, right? Just some hands-on technician work to work. Talk to him and be like, hey, can I come out when we go to do a test program with Astrobotic, right? So if you guys have a payload idea or something like that, or you have a professor that's working on something in that realm, that's the great way to be part of it, right? You could be part of a real funded campaign process to go through the whole, that's where, and most of the time if a student gets in, they're part of the technical interchange meetings, right? Especially if they're integrated in the TIMS, and you're gonna have those regularly, so you're walking through all of the technical side of it, and then ideally you come out for the integration and the actual campaign, you get to watch the rocket fly, de-integrate, so you get to see a holistic process of how a whole campaign goes. And the way that we do it here is one of the things we specialize in is extremely rapid recycle time. So we can get on contract with someone, depending on the readiness of their payload is usually what's holding us off. But if they're ready to go, we can we could go fuel up the rocket and fly tomorrow. Well, we're going to go fuel up today and we're going to fly on Tuesday. So, right, that's the way that we do it. So it's a very kind of 2-week campaign window typically when you come out and you're going to do 3 flights in 2 weeks on one vehicle. But you get to see the whole process of through integration, development, all of that, flight, and probably data review, you know, depending on what you do for the thing. But I mean, that's probably, other than an internship, that's going to be your next best way to be integrated into a whole thing with us. Yeah.
I want to add one thing too, maybe just a bit of life advice, career advice kind of thoughts. Never be too proud to do anything that needs done. If you were, for example, to make friends with that professor, get out here, get on a team, be the one that's carrying the bags, be the one that's filling people's water, be the one taking notes, be the whatever it is that needs to get done. Never ever say that's not my job. Just do it. Pick up the ball, run with it. That's how you're going to catch the attention of the right people. That's how you're going to hear and see things that you might not have been able to hear and see otherwise. That's how you're going to find that you're at the right place at the right time for the right opportunity that you didn't even know existed. So make those friends, make those connections, volunteer to do almost anything that they need, and just integrate yourself into any team in any role.
I love that. So maybe now we'll take some questions. Thank you both for this session, and yeah, we'll take questions.
Propulsion for the landers, he's asking if that's here separate.
Yeah, actually, right now here at Mojave, many people don't know this, but so Astrobotic launched the Peregrine lunar lander back in December. Peregrine survived in space for a long time before we had to bring her back and burn her up in the atmosphere, so she was not quite fully successful, but a wonderful attempt at a lunar landing. Griffin is our next launch, and Griffin is being built here in Mojave in our clean room. It is not the real Griffin that's going to launch. The real one is being built in Pittsburgh right now, but a twin of Griffin, specifically of the propulsion system, is here in Mojave in our clean room, and I'm actually the program manager over that build and over that test. So we are taking that propulsion system out to X Squadron in Victorville, and we're going to be doing some throttle testing out there. Then we'll be bringing the test article back here to Mojave, where we're going to be doing some cold flow testing through the systems. Anybody listening closely, you might immediately have an alarm going off in your head. Hypergalls, danger, danger. Absolutely, danger, danger. Right, so we're doing real testing of real propulsion systems on real lunar landers here in Mojave.
Any other questions? Yeah.
If you have a good answer to that, you'd be a very rich man. No, right? That's every company has their own posture, right? That's kind of what it's going to come down to. You know, there's some companies focus more on rapid iteration and testing, and that's kind of been our philosophy too, right? I'd rather make a decent design, break it, because it's going to break the first time, very likely, right? You kind of want it to break because you know where it failed and you know where you need to do it, right? So it's a healthy blend of doing enough analysis that you've got something that you think will probably mostly work, but then you got to get out and test it. And you got to fix all the niggles that are really going to get you outside of all the valves, let's just say, right? It's always valves. So, right, you've got to figure out, you know, and validate what your actual pressure drop through your lines are, right? All your incompatibilities. You're going to find out your CAD model doesn't stack up, or you can't access a bolt because you put it in a bad spot, right? Those are, and you're going to look over it. That's going to happen, right? And so I think for the most part, our posture and some companies too that seem to do well have that posture of like, try to build something the best you can the first time, but go out and break it and then just do it again, make it better and keep iterating on it, right? So part of that, you're either paying more in overhead or you're paying more in labor, right? So it's where does your company want to spend it is what it's kind of coming down to, right? And what their philosophy is on tolerance and risk, right? So if it's human related, there's a much different risk posture you have to be considerate of in the initial design, right? And everything like that. But if it's just science payloads, things like that, you have a little bit more leeway. And companies have a lot more leeway than NASA does in general, right? NASA, that's kind of a zero risk tolerance, right? They've had that for a long time, and that's part of what their stranglehold is.
Yeah, so I have two immediate thoughts to that. First, V&V is vital. So V&V, verification and validation. If you have simulators, software programs that are verified and validated, then that is an immediate risk buy down early on in your design. So if you are working with validated software models, working with validated simulators, then your risk posture is already in a much better place. And then the next thing I would say is we had a statement in the Air Force, fail early, but recover quickly. So it's not enough to say, go out and take some risk and fail. It's go out, take the risk, fail, and recover. So in order to recover from a failure, you have to have a very good, very robust failure analysis system, failure analysis planning. That entire process needs to exist long before you ever step foot on a test range with something that you are likely going to fail on. So that kind of, it feels like paperwork, it feels like processes that are stopping you from going to do the fun things you want to do, but it is what's going to save you in the future. And it's what's going to keep you funded and keep you running.
So CLPS was their first iteration at trying to do commercial integration, right? That's only lasts through the end of the decade, I think, right? And the thing with the contracting is, you know how contracting goes, it's several years to get to a point. So I can't talk too specifically, but there's more iterations they're gonna have to do, right? Because they learned a lot in this whole process too. It was a first time thing to learn, right? Originally they were like doing, if you remember the name of the 19C, 19A, they wanted to do multiple CLPS missions a year to multiple providers. Didn't pan out the way they want. There was some, global pandemic stuff that happened at the beginning of that. Just didn't help anybody at all. But their initial kind of reaction to was to be more iterations than they have, and I think that's still the goal. But I'm not a specific NASA spokesman, but I know that they're going to work on another version that'll hopefully improve from the downfalls of the first version.
Any other questions? Maybe we'll take a couple more.
I want to add on the personal side real quick. I want to first encourage you guys to please feel free to ask non-technical questions. That's absolutely okay too. Stefan and I have been where you are right now, right? We've been on that cusp of adulthood and that cusp of making these big decisions. So on a personal side, I will tell you, I did get married in college, and I did have 3 children in my early 20s. So back-to-back children when I was 23, 25, 27 years old. And that was when I was active duty in the military. And so I was able to find a balance for how to continue a professional career and how to have a family life. It's very difficult. There's no right or wrong answer. The balance for me is very different than the balance for you might look like, but that is absolutely a possibility, and it's not something that you should feel like you have to choose one or the other. I'm here to encourage you guys. You and only you get to define what you want your life to look like in all aspects of your life, and you do not have to give up one thing just to excel in another. Please, come talk to me personally if you want to ask more private questions. I'm 100% on board with answering those questions because I think that's very important. I have a son in college right now, and I'm watching him on the cusp of making these decisions too, and just encouraging him that where he defines his balance is what he needs to focus on.
Yeah, I can add to that because I'm kind of the opposite spectrum. I'm 38 years old and I have a 1-year-old girl. Only one child so far. So I waited a long time. Right, again, like Samantha said, there's no path to perfection, so to speak. What I will say is, like, I spent a long time after I didn't go to college till I was like 24 years old. So I had a lot of fun in my 20s. So it was a little bit, I didn't talk too much to my history because some of it, you know. But I will say, and she spoke to it before about every job that I've ever done. There was one time when I was in school, I paid for my college myself. I'm one of 8 kids. My youngest sister, who I had custody of, just graduated college, which is really exciting. So I helped her get through college, but only 2 of 8 of us went to school. And when I was in school, I had 6 W-2s at least every year when I'd file my taxes when I was in college. I did like everything ever you could ever imagine, from bartender to selling things on eBay, like everything you could imagine, right? And so what Samantha said, which is true, is, you know, if your name is attached to something, just do it well. Because if you're willing to do things that don't have the prestige or the credibility that everybody's proud of, and you do that well when nobody's looking, when you go to be in a position where it does matter, you've already trained that skill set into you, right? I've been a bartender, I've been a server, I've worked at McDonald's, I've worked at Safeway, right? I've done so many different things, but I've never felt that I was above that thing, because there's always something you can take from that, right? Whether it's interpersonal skills, developing things, having respect for other people that are in customer service positions, right? Because they're doing something for you. And realizing that not everybody has had, you know, the path to get to where they are. So just make sure that you do whatever. So, you know, if you get out of here and you graduate and you don't know what you want to do and you want to go work abroad and work in a surf shop in Thailand, be the best surf shop Thailand guy there ever was, right? Whatever, right? Anything like that, you know. It's a non-linear route to where you want to go, and all the things that you can do just build to your character and your skill set, and those do translate to real skills in the world. So I can't reiterate that enough from what Samantha said. Well, so yeah.
Well, thank you both, and thank you to the audience for participating. We'll end the session there, and we'll be happy to take questions offline too, right? Sure. Thank you.
Oh yeah. You want to pull the chair down? Sure.
You've all been officially released until 12:30. We have sandwiches for everyone, and probably way too many. Feel free to go back, work on rockets, chat. We will also have t-shirts finally arriving, so we can get those to you too soon. So, thank you.
immediately start. So, my name is Piotr, and today I will be presenting this presentation about our avionics system that we've been developing throughout the last year at AGH Space Systems. But first, a little bit about us, because some people might not be familiar with our activities. So our association at our university is dedicated to the development of space technologies involving sounding rockets, planetary sounding probes, such as the CANSAT competition planetary sounds, Martian rovers, stratospheric balloon gondolas, and propulsion development with new and innovative propellants. Throughout the last years, we've participated in many rocketry competitions, some organized in Poland, some organized in the United States, such as the Spaceport America Cup, and some organized in Portugal, such as the European Rocketry Challenge. This is our picture from last year when we participated in Spaceport America Cup with our hybrid rocket 3DK Plus. And we're continuing our journey with rocketry, this time with a liquid propellant, bipropellant rocket called Turbulence. This is a schematic of the rocket and a basic render from the CAD software. So basically, Turbulence is a slightly innovative project. It features a bipropellant tank that houses both the oxidizer and the fuel that are divided from each other using a piston that is pressurized by the self-pressurizing properties of the nitrous oxide. And part of the Turbulence's development is the development of the avionics system, the flight computer for the rocket. So our previous flight computers over the past few years were starting from very basic designs, such as the ones that you can see in this picture here. Basically, a couple of PCB boards fixed to a balsa slab with a couple of screws connected with some random wires, and it worked. It was functional. It was doing its job as it was expected to. However, this had it proved to be very problematic in some areas, such as the modularity of the system, the ability to expand it with features that were not previously thought about during the design process, and things like that. This is also very chaotic, as you can see, and wastes a lot of space. So yeah, it was problematic back then. Later we moved to a more organized design, more advanced and complex design, involving some modularity, such as you can see here. This is the avionics stack that was used throughout some of the Spaceport America Cup competitions and European Rocketry Challenge. This flight computer flew with us for a couple of years with some modifications and improvements over the years. It was composed of several vertically stacked PCBs, each of them serving some kind of different role. However, it had its disadvantages as well. This is very nice in terms of modularity, in terms of the expandability of the system. However, if something goes wrong with one of the boards somewhere in the middle of the stack, to change it, to replace it, requires to disassemble the stack, all of the boards that are above or below, depending on how the mechanical assembly is performed. So it also introduces some lag, some time that is necessary to perform such a maintenance task, maintenance activity. And this is really problematic because it's really hard to do it on the launch pad. It was impossible in this kind of design to do it on the launch pad. So usually if something went wrong with one of the PCBs somewhere in the middle of the stack, or even somewhere in the top of the stack, it usually meant that the launch is scrapped for the day, and there's no possibility to conduct the launch during this day. It was necessary to scrap it, to go back to the motel, to the hotel, and perform maintenance, disassemble it, assemble it again with replacement units, and this sort of stuff. This design also had some flaws in terms of the robustness for some random events, such as one of the boards burning out, some component going over current and frying random traces and random components on other parts of the stack. So it was better, but it still had some issues. And despite the fact that we've worked very hard over the past years to improve it and eliminate as much of the disadvantages as we could, ultimately it was better to finally move on, to finally design something that uses and utilizes our experience that we've gained over the years with working on this project, and design something new, something better. So our key requirements for the new design were as presented here. First is the robustness. So we had to emphasize the fact that this new flight computer cannot be easily influenced by the high temperature on the launch pad while waiting a couple of hours for launch for some random reason. Of course, not every being waiting for the winds to come down or having to move our launch rail a couple of degrees lower. Yeah, but but basically it had to survive long time in high temperature. It had to be able to survive high vibrations and other mechanical and electrical harsh conditions. Safety of operations, which means that we had to emphasize the ability to minimize the risk of some random unexpected event happening with the system that we are unable to control, we are unable to encounter in any way. Another thing is the ease of repair and replacement. So we really wanted to eliminate the necessity to disassemble the entire stack, the entire assembly, to perform maintenance on one of the modules. The versatility, which basically means that we want to be able to use this flight computer for many projects, not necessarily only the turbulence rocket, but other projects, maybe even much more complex ones. And it had to be optimized for batch manufacturing. We really wanted to be able to manufacture many units at a time so that we are able to have many replacement units on site, on the launch pad. If something goes wrong, we must be able to quickly replace it and be able to launch in a short time. So the architecture of the system is as follows. There are two main units that we named after the veterans of our association, the members that are long gone, but all of us remember them, so Agatka and Bartek. This little couple serves the main purposes of this flight computer. Agatka is the data acquisition, control, and radio communication module, and Bartek is the power management module. As you can see, Bartek takes power from both the internal batteries and external power source available on the launch pad, and uses the external power source as long as possible, which basically means that as long as the rocket is physically present on the launch rail, it uses the external power source, which can be provided indefinitely from, I don't know, a power generator, and external batteries, car power from the lighter connector, and anything that you can provide externally, Bartek can take and can use it to power the rocket as long as it's present on the launch pad. Bartek also provides power for the mechanical actuators, in case of turbulence, the servo valves. But Agatka is the brain of the system. It controls the actuators by sending proper commands. It takes inputs from pressure transducers, from the magnetometer array that we use to measure the position of the piston that separates the oxidizer and fuel inside the bipropellant tank. And it also provides the radio communication, two-sided radio communication with the ground station using FLRC and APRS. And it also is able to connect to other modules inside the rocket using the CAN bus. So as for the system architecture, for the software part, we are using the FreeRTOS real operating system as the basis for our framework for our firmware. And our microcontrollers are, as usual, the STM32F4s, specifically the STM32F446. We have developed firmware for them over the past 10 years. We are really familiar with them, and we feel comfortable working with them, and specifically we feel safe working with them, as we know most of the caveats of this technology. As for the design tools, we used Altium Designer for the PCBs and STM32Cube framework for working with the STM32s. Not much to say here. So let's talk about Agatka. This is, as I said, the data acquisition, control, and telemetry unit. It uses the STM32F4 microprocessor, and as you can see here on the schematic, it has a lot of functionalities. The most important ones being the RS485 transceiver, which enables us to talk with our servo actuated valves. The I2C extender, which provides good and more robust interference communication with the magnetometer array to measure the position of the piston, and the analog to digital converter, which enables us to measure all of the current loop devices, in our case the pressure transducers that inform us of the state of the pressure vessel. As you can see here, we also have the RF transceivers, lots of other stuff such as the inertial measurement unit for state estimation. We also have some power protection features such as the e-fuses and some low dropout regulators to create specific voltage ranges for specific components on board the Agatka module. For data acquisition, we have 5 pressure channels for the 4 to 20 milliampere current loop, some pressure vessel temperature channels. The Hall effect sensor array can take up to 128 magnetometer sensors to measure the position of the piston precisely. We have some inertial measurement channels such as the accelerations, the gyroscopic rates, and some internal magnetometers, as well as the ambient pressure channels to perform some additional recovery related calculations. As for Bartek, the schematic is also quite extensive. We are using several DC-DC switching converters to provide specific power rails for necessary equipment, such as the servo actuators, the normally open valve for emergency venting of the pressure vessel. We have some logging capabilities, such as the SD card to log power-related data. Also, a microcontroller STM32F4 for intelligent management of power. And one of the key components of Bartek is the power path controller, which allows us to dynamically change the source of power for the rocket without any intermediate crashes of the system. So even if the external power supply is ripped apart from the rocket, it still maintains its working state as before, as it was, without any interruptions in the system's performance. As for the assembly, we made a simple backplane PCB, which allows the 2 modules to be connected together, and it also provides connectors for external power, main power, and 2 harnesses that connect the flight computer with the rocket's insides. This is the mechanical assembly with the avionics compartment designed by the members of our mechanics team. So here you can see some interesting features, such as our custom battery composed of lithium-ion cells. Also, you can see some rails on the side of the avionics compartment that allow this enclosure to be slid into the airframe and twisted to lock in place, and then it can be secured additionally with some screws. But generally, it stays in place without any additional tools. Of course, we will use screws for making sure that it stays in one spot and doesn't move around, but it really speeds up the integration of the rocket. For ground control, we also made sure to make everything compatible with our great and fantastic piece of software developed by our magnificent colleagues from our software team, which is called Grażyna. This piece of software serves us throughout the last 7 years, and we really love it. We are grateful to our friends from the software department for it. As you can see, we can control most of the systems inside the rocket, see the states of the pressure sensors, of the load cells, and any devices like this inside the rocket in real time. So, yeah, thanks to our friends from the software team. To sum up the presentation quickly, because I see I'm close to running out of time, the key advantages over the previous FCs are the modularity. We can easily swap the modules and design other modules that serve different purposes and are compatible with the same backplane connection mapping. The ease of access, selection of components with long-term availability, so that we will, for the next 5 or so years, we will not encounter a problem where some components went out of the production line and we cannot source them, so we need to redesign the system. Hot swap capability, which allows us, if such access is provided, to replace modules without shutting the system down. Multiple backup communications between modules on a backplane. In case one fails, the modules still can talk to each other. Single standardized connection mapping, as said in the modularity part, and extensive ESD, overcurrent, overvoltage, and thermal protections, which make sure that our system will not be impacted by any harsh conditions that may be encountered in a hot desert environment. For testing and evaluation, we are always performing firmware on-commit tests with continuous integration, continuous deployment, unit tests, integration tests. For hardware peer review, we made sure that many members of our avionics electronics department will perform the review over the hardware before it is sent to manufacturing, and we are planning to do some component hardware in the loop tests, system level stress test, and robustness tests that will involve vibration tests, high temperature system performance tests, and high temperature battery life tests. For future development, we will develop various backplane versions to conform to other rocketry projects. We are planning to develop additional modules for features that are not required by the Turbulence project but might be required by others. And we want to design a plug-and-play testing backplane with 16 module slots and adapters for lab equipment so that we can plug multiple modules into it and have a testing setup inside our lab. Thank you very much, and if you have any questions, I'm happy to answer them. Thank you.
Come. Oh yeah, just say it and I'll repeat it. So I'll repeat any questions that folks have here. Just let me know. Wait, actually, could you come up? I can't hear you. Just away from the thing. Yeah, you're good.
I was wondering about the magnetometer array that senses the piston position in the fuel tank. Like, sort of how it's set up. Is it like a string of them with a magnet and the piston or something?
Yes, if I heard the question correctly, then yes, the piston has a strong magnet, strong neodymium magnet that is connected to one part of the piston. And the magnetometer array is basically a large number of magnetometers on dedicated PCBs that are daisy-chained on I2C bus going vertically throughout the pressure vessel with one of the internal tubes that goes through. This tube is also one of the rails on which the piston moves. And each of the magnetometers senses the spike in the magnetic field when the piston is nearby. We are using this data that we gathered during a calibration to to then perform some algorithmic stuff that the software department is responsible for, and this gives us some kind of transfer function that provides us with the ability to know where the piston is with sort of 1 to 1.5 millimeter resolution.
Interesting. Thank you.
Any other questions from folks? All right then. Thank you very much. Really appreciate it.
Thank you.
Okay, then we'll see you all around. All right, we're gonna take a break for about, I wanna say 30 minutes. We're gonna move presentations back. Partially, it's because there's going to be an F-18 landing. It's gonna be very loud, and I don't want anybody's presentation to be interrupted. So, I'm just gonna move back 30 minutes. In that time, I wanted to invite any VAST folk, just so you're aware. VAST is here, VAST is there. Talk to them. They're wonderful people. They're hiring a lot of people and a lot of new grads, so you should check them out. And also, you got some engineers from VAST over there. They've been looking around your stuff as we've been talking, so talk to them. Unroll your posters if you have a rolled poster back there, whoever that was. Show them what you have. Pardon? What? Well, yes, F-18. It's gonna land. It's gonna be loud.
That's my laptop. Okay, that makes a lot of sense. It's my laptop.
That's his laptop?
Yes.
No, it's my laptop.
No.
Oh, that's my laptop. Here you go.
Oh.
Yeah.
You not have to step on it. But yo, what you got? Occupy Mars.
Why aren't we on featured speakers?
Why aren't you on featured speakers?
Yeah.
Because
It's kind of messed up.
I'm sorry. My brain's like. Because we'll send podium presentation information literally last week.
Oh, really?
Literally
last week.
Somebody did it last week, somebody did it this like Monday, and then somebody did it last night, and I was like, turns out I'm awake anyway, because I was driving somebody from Lancaster up to California City.
I guess.
Yeah, like a hello, like here-ish.
That,
Okay, you guys are.
Hello. Hello.
Okay. Cool. I wanna do something. Okay. Huh? I don't know. Outside? Yeah. Okay. I will go outside and get people. Anybody near the door, if there's any folks outside, can you tell them to, 1, come back in, and 2, come back in. Thank you. We're going to start with Columbia's podium presentation in just a moment when we have your attention. So please come and sit down if you would like to listen. Otherwise, I don't know what to tell you. Pardon? Yes, we're recording all of it.
Yeah, we can. Yeah, sure. Yeah, just give me your email. I can send it to you. Okay.
Where's most of the Columbia team? Oh, they've moved. Okay.
Yeah. Just spreading out.
Mhm.
Like half the conference office.
Where's
I wonder if like Alex actually needed a fingerprint today, or was he just saying?
He's probably just doing it. He's like, Adam needs a task to do, and then just added something up.
Yeah, I had nothing to do last
and
night.
then-
Dude. I was so like, I had nothing to do last night. I was like, dude, I need something to do.
Dude,
So I
you both just slept. You just sleep. That's what I do. Just slept. This is so annoying.
think we just start.
Should we?
We got 1, 2, 3, 4, 5.
If we start, they'll probably come. It'll just be too loud for them to speak, you know?
Yeah. I think we should start.
Alright, you got it.
Should we start?
Okay. George, should we just start?
Okay, I'll announce you, and then we can begin. Yes. I'll just read out the title of your thingy, unless it's changed, but I think it's the same. Whenever you're ready. It's been? Okay. Okay, hello everyone. We are going to get started here. Again, if things get interrupted, please be mindful of that. Like, okay, cool, we'll pause, but we'd like to just continue going. Columbia University is going to present a presentation on coaxial pneumatic valves for hybrid rockets. Take it away.
Hi everyone, my name is Adam Awad. I am a rising junior at Columbia, and together with
Skylar Bogdanovich, who is also a rising junior at Columbia.
So we were fluids leads this year for our hybrid rocket, which encompassed everything from the oxidizer system, run valves, ground support, and quick disconnects. So a quick agenda for our podium presentation. First, we're going to talk about the valve performance. Then we're going to talk about the mechanics of the valve, materials, manufacturing, which is mainly CNC machining, and then iteration to get to its final form, which is sitting over there. So quick introduction to the valve performance. So why did we need to build our own valve? So at a high level, amateur rockets without active guidance require very high thrust-to-weight ratios. These engines must be designed to have high thrust and low burn time for the equivalent impulse range. And this means for hybrid rocket engines that we need extremely large mass flow rates through the main oxidizer valve. So the main role of the run valve is to open at engine startup after the igniter has been burning. And this enables full thrust. Before this state, the igniter is just building a flame front in the engine. So we need to open the run valve and start dumping the nitrous from the oxidizer tank into the combustion chamber to generate thrust. So here's a quick video of our old ball valve, which we'll talk about in a second. This had a servo-actuated ball valve with a linkage arm. And you can see the transition from ignition or from the igniter lighting to full engine ignition. So at this point, the igniter starts burning, the valve opens, and now we're producing thrust. So this is the goal of the nitrous run valve.
Yes, so to go quickly over what we were going before, our old valve was the ball valve. And the good thing about the ball valve was that it was very reliable. And the reliability ultimately caused us, or resulted in our success in a launch last year. But negative parts of it was that it had a very low mass flow rate, so ultimately it was constricting our flow, leading to an ultimately lower impulse or lower thrust, and a slow actuation time also contributed to that as well. And ultimately it was made out of 316 stainless, as well as also included a 125 kilogram centimeter servo. Both of these things lead to a very heavy run valve, and also required a bunch of fittings and a very long, a lot of length, which also adds to the mass as well.
So you can see just how long the legacy system was, and if you take a look at our current system, which is over in the back, it's a step improvement, and that both in compactness and in total performance. So some high-level requirements for the valve design: it needs to support at least a 2.29 kilogram per second nitrous oxide mass flow rate. We also built in some margin for future-proofing so that we could reuse this valve for larger engines in the future. It also needed to achieve sub-second actuation. This would maximize our acceleration and make our vehicle more stable. It needed to be lightweight, as we talked about in the previous slide. Stainless steel, large servos. These are heavy components which will decrease our vehicle performance. So we needed it to use lightweight materials that would support a higher, more capable vehicle. Finally, it needed to be compact in both axial and radial directions. This is to minimize vehicle length as we increase our oxidizer tank length to improve vehicle performance. So we wanted to make it as short as possible, and we wanted it to be fairly narrow so that we could fit fill valves, pressure transducers, and other hardware in our inner stage. And lastly, all components need to be available commercially for cheap, for budgetary reasons, or need to be machinable in-house. So some acceptance criteria for the valve, so we could evaluate if we did our job properly. We needed to have a low leakage seal. This is pretty obvious, but we didn't want it leaking nitrous. This would slowly decrease our tank pressure over time and could introduce a lot of oxidizer into the combustion chamber during that time between the igniter being lit and the valve opening. It also needed to enable the target mass flow rate. This is the main constraint and the goal of the valve. If it's too small and we can't hit our target mass flow rate, then it didn't accomplish anything. It also needs to have a less than 10 psi pressure drop. This is to maximize our combustion chamber pressure and minimize our nitrous tank pressure. And it needs to be lighter than commercially available solutions and compact. So this is some of the acceptance criteria of how we determined if we did our job properly building this valve. So a quick overview of the mechanics of the valve. I'll explain how it works, some of the calculations that we performed to size it, and how we found relevant parameters for performing simulations and FEA. So early ideation of the valve, the design is loosely based off of the Waterloo coaxial valve and similar coaxial valve designs, which use a piston compressing on a PTFE ring that is then pushed upwards by compressed gas, at that point breaking the seal and allowing flow in this channel here. So I'll go into more depth about how this works, but this is just a quick doodle on how we establish the high-level parameters to then design the valve. So the components of the valve, we have this part here, which is the piston. This is the only moving part in the entire propulsion system. And at ignition, the nitrous vapor pushes the piston up, and we have nitrous flow. The valve body holds the piston, the inlet for the nitrous, and also interfaces with every other component like the seal seat and the integration ring. The integration ring has the upper rod seal, which is critical for making sure that nitrous stays in the oxidizer tank and doesn't leak through this O-ring right here. And the valve body also has another O-ring here to make sure that when we actuate the valve by pressurizing this area, it doesn't leak into the injector and we don't get actuation. The spring provides static compression of the piston to seal at when we start filling. There's additional force here at the top of the piston. And the seal seat holds the PTFE ring retainer, and also has channels for flow. So you can see here the mechanics of how the valve works. During fill, it has static nitrous just sitting in the valve, and their seal is formed at this point here. Then when we're ready to launch or static fire, the pneumatic valve solenoid opens, nitrous vapor flows into this cavity, pushes the piston upwards, and nitrous flows around the seal seat into the injector. So here are some pictures of the final valve, so you can get an idea of what it looks like. This is the valve integrated with the combustion chamber. So it has a flange at the top, which mates the oxidizer tank, and another flange at the bottom, which mates the injector. And this is the valve in really cold conditions because there was some leakage. So quick overview of the design parameters. One of the main goals with the valve, of course, was to have it actuate successfully. So we need to find the force balance. On the top of the valve, there is hydrostatic or static pressure from the nitrous that is compressing it and is counteracting the actuation force. So we need to characterize both the actuation force, which is on the piston OD flange, and the static pressure on the top to make sure that it can overcome these forces and actuate successfully. And there's additional spring force and O-ring friction, which will also be discussed. So it also had a double acting capability, which means that if we wanted to, we could also pressurize the top for additional compression. We didn't use this capability in our final vehicle because it simplified operations and the spring was more than enough to seal, but it allowed more agility in the design. So for calculating the force balance, we just use these two simple formulas. So the cavity radius is the OD of this piston. The piston radius is this OD right here. And then the difference between that and the static pressure on the top, which is just equal to the thickness of the piston, gives us the total force pushing the piston upwards. So another key thing that we had to account for was the O-ring friction. So we used an empirical model for calculating O-ring friction, which had two components, compressive friction and hydraulic friction. So compressive O-ring friction is characterized as the squeezing of the O-ring when it's initially installed. So this doesn't vary as a function of pressure. It just has empirical coefficients associated with the O-ring dash number. And so this was one variable. The second variable is hydraulic friction, which is based on O-ring extrusion under pressure. So this increase is a function of the pressure across the O-ring. The higher pressure, the more the O-ring would extrude into the gap between the rod and the piston, and this would increase the friction. So this was a first order model. It was not 100% accurate in our testing, and this was in part because we lacked the expertise to control things like surface roughness, lubrication level, and other variables during machining and integration and test. And this is one of the restrictions of our team, but despite this, we still built in enough margin that the valve worked successfully. So finally, to calculate the actuation, combined Hooke's law for the spring, the O-ring model, and the piston force balance, and wrote this code in Python, which uses a really small time step to calculate the acceleration of the piston and give the final actuation time, which was 17.5 milliseconds, and the velocity at the hard stop, which was 56 feet per second. We then used these values to perform CAN calculations and FEA to make sure that we wouldn't be deforming any components or damaging the valve during actuation. So we also performed simulations in ANSYS Fluent. So you can see here is a flow path of the simulated particles. We simulated compressible and incompressible flow and found a simulated pressure drop. However, we were fairly limited by the student version of ANSYS Fluent doing these simulations. So our main results come from testing. So quick overview of the materials we used. Almost all components were machined out of 6061 T6 aluminum. This is due to a combination of its excellent weight, cost, and machinability. An important caveat is that this material is not as safe with locks or docks in valves because of an ignition hazard, but since we're using nitrous oxide, we deemed this acceptable. Also, PTFE was selected as a seal material It's for a couple of reasons. It has exceptional machinability. It has extensive documentation in the public domain. And the team that inspired us to build this valve, University of Waterloo, also had previous success using PTFE sealing. So we knew that it could be done. Another key part was design for manufacturability. As I mentioned earlier in the presentation, this needed to be machinable on 4-axis and 3-axis CNC machines. We are fortunate to have access to a 4-axis SE20Y and 3-axis mini mill, and we wanted to utilize these machines to avoid outsourcing the components and save money. Knowledge is passed down through successive generations of students. Shout out to Ryan sitting over there. He's taught us a lot about machining. We don't really have a machinist or anything. We just teach ourselves through successive generations and build cool stuff. So we machined all the coaxial pneumatic valve components in-house. This was a great learning opportunity and saved us money. And we also needed to design it to have minimal new tooling and no custom tooling. So this determines some variables like the orifice size, which was selected as 1 inch because this is an easily available indexable drill size, for example. The other material thing that we sized was PTFE. So PTFE is a soft plastic compound, and it's an excellent sealing material. We found some Apollo-era NASA documentation that cited 4 pound-force per linear inch of circumference for PTFE. This seemed like a little bit of a hand-wavy value, even though they cited some testing with helium that supported this as being bubble-proof. So we initially designed the valve for 12.6 pound-force, which is just calculated using that 4 pound-force value. But it also was designed with enough margin to increase the pressure on the PTFE up to 30 pound-force. And then we also selected a spring based on these parameters. So the spring that we selected had a K of 46.6 pound-force per inch, free length of 2 inches, and a compressed length of 1.325 inches. For context, the valve stroke is 0.5 inches, so that other 0.175 was margin for increasing the spring force. So manufacturing.
Yeah. All right, so first thing we worry about manufacturing is tolerancing. Ultimately, sealing surfaces had to be around 5 thou profile tolerances based off Parker O-ring handbook. And then we applied maximum material condition and least material condition where necessary, talk about it a bit later. And ultimately, some tolerance stack up did cause some leakage and iterations later. Yeah, so as talked about before, material we're using is 6061 aluminum. Every component was made in-house. All of the components were basically designed to be used on our 4-axis lathe, as you can see on the right. That is during one of the operations. And actually what happened is the lathe we were using kind of was majorly out of tolerance, ended up actually just like shutting down, so we couldn't use it. So we had to find a lot of fun workarounds and basically solutions to that. Ultimately, we ended up building a bunch of jigs so we could then convert our components and use them on the mills. As you can see in the bottom left here, this is one of the jigs we used. This is for the main body. So it would match the circular contours, but then we can still use the flat surfaces in order to grip into the mills. One problem we found with that was that probing and getting it perfectly perpendicular to the surface it was on was pretty difficult, as any sort of slight angle would be significantly different as you get deeper down because you're probing on the top surface. So ultimately we would use indicators, which are very difficult and very repetitive process to get a very perpendicular surface. And as you can see, this left indicator was broken after a lot of repeated usage. Another thing we had to work around is because we couldn't use the lathe, O-ring grooves are very essential part of this design, so we couldn't just use a grooving tool and create that. So what we did is use these things called key seat cutters, which you can see on the right there. You could put that in the middle and use a circular contour to effectively create the grooves, which worked quite effectively. Yeah, so now on to iteration. So there was two major components of the valve that we wanted to test. First was the sealing, capabilities, and then also the actuating capabilities. So as you can kind of see here, this is us assembling the valve in the middle. On the right is it fully assembled. On the left here is us during testing, as we conducted many hydrostatic tests to see whether leakage was present, and we'd see water buildup right here if there was leakage. So our first test we conducted was a hydrostatic test, and we pressurized to around 1,000 psi. And ultimately, our main seal, the PTFE seal, did fail, and we found some major leakage there, which was the main problem. But it did validate the rest of our structure, as nothing else broke, and all the O-ring seals held the pressure effectively. So you can see right here, this is the piston right here, and this is the PTFE. So we're going to be mainly looking at these two things and how they connect to create the seal. And you see in version 1, see how that is. And then after the first test we failed, our first initial thought was to create a spacer and push up the whole assembly up more. So that would ultimately put more force into the spring. So that would put force that down into the PTFE, creating a larger force. So you can see where the circles are, where we added the spacer to create more force. And after hydrostatic testing that again, unfortunately that did not work. It did not significantly change our valve performance, and there was major leakage across this PTFE seal. So after consulting different teams that had built similar valves before, we found that our main problem was the contact area between the piston and the PTFE seat. So before you see how the piston and the PTFE both are at a 45-degree angle, so there's a large contact area between those two surfaces. What we did to change that is we changed the angle of the PTFE seat in order to effectively create one constant radius of, or like a knife edge, into the PTFE that would apply all that force and effectively create a seal. So as you can see here, the outer diameter of the piston is the only point of contact with the PTFE. So in theory, that would force it down and then effectively create a seal. But we tested it again, and unfortunately, the sealing got even worse. And after some investigation, we concluded that the outer diameter of the piston was hitting the aluminum due to some tolerancing issues, which goes back to the lathe again. So for our fourth and final iteration, what we did is instead of changing the outer diameter of the piston to hit the seal, we wanted the inner diameter of the piston to hit the seal. So hopefully you can kind of see the angle change so that the PTFE is at a lower angle than the piston. So it had that one constant circle of radius hitting the PTFE, forcing a lot of pressure on that one point, creating an effective seal. And after hydrostatic testing this again, it succeeded and fully held pressure with no leakage. So the second part of the valve we wanted to test was actual actuation. This ultimately makes it a run valve and allows our nitrous oxide to flow through, so this was obviously essential. And when we first tested it and we pressurized it, nothing actually moved, unfortunately. But after playing around with a bit of components, we found that if we remove the integration ring, which is this top ring up here, then it actually actuated successfully. And after some measurements, we found that the top of the piston right here and the inner diameter of the main body were actually not concentric, and they're around 20 thou off. This goes back to our machining issues, and ultimately was something we could hope to get in tolerance but didn't hit. So our fix that we decided to do was actually just widen the inner diameter of the integration ring. So we widened that by around 10 thou diametrically. And ultimately, after testing it again, it did successfully actuate. And I believe a couple of days after that, we brought it to our first fire, and it fully actuated, significantly increasing our thrust.
Okay, so a quick discussion of the testing results, just validating that our pneumatic valve worked as designed in our static fires. So the main improvement was we went from being too cold to being too warm. So really proud. So this is a picture of the pneumatic valve integrated. This is a picture of a cold flow, which we used to validate that the mass flow rate was correct. And then this is a picture of a static fire. This is like my favorite picture. So you can see the mock diamonds and the burn through at the same time. So great picture, Ryan. So just a little bit of data. So main things that I want us all to pay attention to is this point right here, which is showing the blowdown curve. So you can see the aux transducer is upstream of the pneumatic valve, and the CC transducer is at the injection manifold, which is downstream of the pneumatic valve. So if you look at where the aux transducer is, we're starting at about 690 psi and decreasing, whereas at the CC transducer, we're starting at 600 psi and decreasing. So we're looking at a 90 psi pressure drop across the ball valve, which was our old solution. With the pneumatic valve, we're looking at an initial starting pressure of around 650 psi, and we're looking at even higher pressure downstream of the pneumatic valve. So clearly something is wrong here. This was an instrumentation error, but it does show that at least there's not significant pressure drop across the pneumatic valve. And more importantly, we hit our target mass flow rate, we hit our target thrust, and and it actuated extremely quickly. So future work for this valve, we want to properly characterize the pressure drop. So the data from static fires shows an unphysical result, which is an increase in pressure downstream of the valve. This is almost certainly an instrumentation error or a sensor error. We're going to do flight testing tomorrow and potentially add throttling. So enhance the double acting capability to make the piston move and control the throttle response. So any questions? Yes. So the goal is to minimize the pressure drop as much as possible. We targeted less than 10 psi pressure drop in the acceptance criteria. Now, we don't know exactly how much the pressure drop was because of the aforementioned error with the pressure transducer. We can't pinpoint exactly what it was, but we do know that it allowed us to hit our performance parameters and was not choking upstream. So we hit that almost exactly the perfect mass flow rate across the injector after we made the upgrade to the pneumatic valve. So yeah, that's something that we can characterize with future work. We kind of ran out of time this year, but an improvement to be made for next year. Yes? Sorry. Yeah, so the main goal was, so for determining the mass flow rate across the valve, we mainly wanted to make sure that the injector was choking. So the injector has, I believe, 72 orifices, and each of those are like 1.7 millimeters in diameter, I believe. So the most important thing was that the injector was choking. Now, when we initially did calculations for the 3/4 inch ball valve, which had a 0.41 OD orifice, that we found that the mass flow rate through that orifice was actually less than the mass flow rate through the injector. So essentially, the valve area needed to be larger than the injector area to make sure that the injector was choking. So now our valve area is significantly larger than the injector area, and this gives us room to scale in the future before we run up against that ceiling again. So we measured mass flow using thermodynamic modeling of the aux tank blowdown. So because our nitrous is in a saturated equilibrium condition, when the tank volume decreased, some amount of nitrous would boil off to replace that volume. And because we know the volume of the tank, and we know how much mass we have based on the load cell reading before the static fire started, then we can back out the mass flow rate as a function of time based on the pressure transducer data. Any other questions? Cool. Thank you, everyone.
I think we can move directly on. We're running a little bit later than thought. So University of New Hampshire, I think you guys are next. Do you want to use my computer? Yes? Cool. Hot sec. Oh my god, I hope this thing's charged. Okay. In the meantime. What a cool valve. Okay. Oh god, do you know how to get out of this? Oh, F11. It says how to get out. It's not even all of them. Okay, you sent them to me, so we're good at this. Thank you. Here's the link. Okay, go for it. Let me just plug this in. Okay. And just hold it. Yeah. Thanks for timing it.
Yeah.
And it's showing up. Yeah.
Working? Cool.
Okay.
Yeah.
I will introduce you as per custom. Hello. Okay, so this is UNH, University of New Hampshire. And they will be talking about IOV2, single board flight controller, and prototype design. Please take it away.
Hi, everybody. My name is Mason. I am the former president and I guess former avionics lead for UNH SEDS, Students of the Exploration and Development of Space. Today I'm going to be going over a prototype design for our first single board flight computer. It's still in development, but we have made quite a bit of progress over the course of this year, so some interesting things to share with you. So just an overview of what I'm going to talk about. First, the concept of operations, how exactly this is applied and how that relates to high-level requirements and features for flight computers in general. This is really general avionics stuff, but for those of you who are uninitiated to avionics, it's pretty cool. So also some design considerations that come up when designing avionics. These factor into lower level requirements later on, which I won't be going over, but they're very important when you're designing your hardware. Our final hardware selection, given those design considerations, and then of course the implementation, how that turned out, and then our current status, and what our next steps are for the project. So, concept of operations is pretty simple. Unless you have a single stage solid motor with a built-in ejection charge, you need electronic deployment, right? So flight computers rely on the use of pyrotechnic charges. This is really simple. And for a two-stage deployment, you have a main event and a drogue event. So at the bare minimum, I need a flight computer that can detect my altitude, detect these, the conditions for these two events, and deploy two pyrotechnic charges. Very easy. But there are a lot of other desirable features that could tend to creep in that you really want for flight computers, especially something like data logging. So going into high-level requirements and features, the must-have here, again, recovery deployment. Safety, that's the whole point of this thing. But should-haves, you really want data collection and logging. For competition, it's required, unless you're using an off-the-shelf system and this thing is purely like perfunctory, you need those. Tracking and telemetry kind of go hand in hand, but there is like kind of a nuance here. Tracking can be single packet per second, something very simple. It doesn't need to be high resolution, but telemetry can be is where your data rate and your frequency of packets really factors in. So there's a lot of trade-offs to be had there that factors into your radio frequency considerations down the line. And then nice to haves. These are where things start to creep in. So state estimation for orientation and position, really nice to have for collecting data about your flight, what it looked like, not just your altitude. Also can be more accurate, and it's necessary for a supersonic flight.
high-speed or bidirectional connectivity are also very nice to have. High-speed connectivity because you get that nice live telemetry, and if you drop out during flight, at least you have something to work with. Bidirectional command and control, you don't exactly need it, but it would be cool. But again, this thing should be autonomous on its own. You can see during the different stages of flight, these features become relevant. So telemetry, data collection, those are relevant across all stages of flight. But my recovery deployment is really only relevant when I'm doing my drogue and my main deployment. Tracking is technically only relevant during recovery, but if your tracking drops out, you really want it going during all stages of flight so you have some indication of where your rocket landed. Active flight controls are a very nice thing to have later on. If you're doing air brakes, doing thrust vector control, just having some way to interface with other boards. That's why auxiliary peripheral interfaces are nice to have. So if I'm running valves, flight control, something like that, it should be important to note that these peripheral interfaces shouldn't necessarily be tailored to your application. So say I want something actuated via PWM, pulse width modulation, right? That doesn't necessarily mean I want to run PWM out of my board straight into whatever, because if I'm going to extend that to other applications, I may not need PWM. I may decide I want something else entirely. So sort of abstracting my interfaces between my board and potential other peripherals is nice, but still having some kind of interface like UART or CAN that can run to other boards is a really nice thing to have. So, under design considerations, we have the classic size, weight, power. These are the big ones. These are often safety concerns with something like power because I need to make sure that my flight computer isn't going to die on the pad. Size is kind of the impetus for having a single board. So I could theoretically take something like a development board, plug it into some kind of primitive backplane with a bunch of breakout boards and call it a flight computer, but it could end up very big. And forget about trying to use screw terminals with 50,000 wires in your avionics bay. So size is a huge concern, just how cluttered your avionics bay is. Weight, not a huge concern with avionics. I mean, the whole bay comes out to like maybe a few pounds unless your batteries are really heavy. So, but it's size and power. On the power side, I may decide that I want to optimize my power consumption with something like a buck converter instead of using a regular linear converter, but that factors into my design considerations later on. Instrumentation. So normally, I'm detecting altitude using a barometer, a pressure sensor, right? Very standard, very easy, but it's not accurate at transonic or supersonic speeds. It's subject to extraneous conditions like my venting of my avionics bay, any interference from maybe leaking from my recovery charge deployment. So like being susceptible to external influences just from air pressure, not a great thing. So I have to consider whether I really want to be reliant on a barometer for my pressure readings or for my altitude detection in general. Many sensors have ranges below common extremes. So for example, a lot of sensors, say an accelerometer, could be plus or minus 16 Gs, right? I could easily see those accelerations if I'm running a short launch rail, either off the rail or later in boost as I'm burning through my fuel, right? So factoring in just keeping an eye out when you're doing your design, am I getting sensors that are high range, but also making sure that my sensors have high enough resolution to get accurate data if I'm doing something like state estimation. And then on the assembly side for implementation, because implementation is a big concern that will come to bite us later, packages for some instruments are very difficult to assemble manually. The name of the game these days is small packages. Like I want a 2x2 millimeter accelerometer, or maybe a 2x2 millimeter 9 degree of freedom IMU, right? That could fit in a smartwatch. But I don't need something that small for a flight computer, but that's what's on the market. So with something like 12 pads on the bottom of that, your instruments are going to be insanely finicky to assemble, by hand, that is. So that's just something to consider, or at least watch out for when you're doing implementation. And then of course, microcontroller selection. So how fast is my processor? Does it have multiple cores? That can factor into your sort of the overall idea of performance for you. And then how many peripherals can it handle? This is a design consideration that factored in with us for something like the RP2040, which I'll get into later. But again, with having those external peripheral connections, I may just use up all of them on my board with the instruments I have and not be able to connect something else in the future. So factoring in whether my board can support a good number of peripherals is important. The big one, telemetry range, data rate, and complexity. Making an RF circuit on your own is pretty prohibitive for, I'd say, the entry level of this. If you're self-taught, if you're not an EE, or even if you are an EE and you haven't taken a course that covers this, it's almost impossible, I would say. So you really are limited to what's available on the market. So old school is 70 centimeter ham. There aren't any, as far as I know, any COTS options, like boards that you can just put on to your board for ham radio. So I mean, you see these on regular COTS altimeters, but they have their own RF balancing circuits that they've done themselves. So in my opinion, best option, 915 megahertz LoRa. It's long range, data rate is configurable. 20 decibels gain is typical, so that's 100 megawatts for transmission. That's not great, but it's something. But 30 is possible on certain designs, although they're not very common on the market. So, and then I have some specific, like tailored COTS options, like the RF3900, very long range, very high performance, but it's a huge board, relatively speaking. Some small considerations, pyrotechnic activation can cause a brownout of the board, so just making sure I have a capacitor on board, making sure I maybe have a diode to protect from back voltage. User feedback, buzzers are preferable to LEDs. LEDs are cool, but once my flight computer is in my rocket, I can't see an LED, so I need a buzzer if I want user feedback while it's in the rocket, and I don't have any kind of wireless connection on the pad. SD cards may seem preferable, but depending on your application, they can be corrupted under vibrational loads. So push-push connectors, the kind that you usually see for SD cards, they don't really retain them well, and any vibration can cause corruption of your data and just loss of flight data in general. So really not a great situation if you're in competition and you lose your flight data due to little vibration. So this is something you need to consider when you're selecting how you want to store that data. So what do we choose? The microcontroller and the ESP32. These are very common for new hobbyist projects. STM32 is sort of like, it's old reliable, and it comes in a very wide range of performances and packages, but ESP32 comes with dual cores, high clock rate, built-in wireless connectivity, and a large number of peripherals. So it's great. STM32, we covered that. It can be a pain to program sometimes. If you're comfortable with it, you have an established ecosystem, great. If you're just trying to get off the ground like we are, you're limited in personnel and experience, it can be a learning curve. The RP2040, actually very comparable stats to the ESP32, but it's somewhat lacking in peripherals, and it only supports a limited amount of external flash, which, if you're using onboard flash memory or an SD card, not great. And neither offer integrated connectivity. So ESP32 is the way to go for us. For telemetry, as you probably could have guessed, an RFM95W LoRa module. Really common, off-the-shelf LoRa module. Not the best range, but highly configurable. I can easily tweak the settings on this so that I get lower data rate, sure, but I can get a really long range. So you could easily go out and do field testing and say, is this acceptable for my criteria? How far away am I expecting my rocket to drift? And go from there and tweak those settings. And of course, it's cheap. So what was our idea for how to organize this? So instrumentation, don't really need to go too in-depth in these, but it's important to note that the accelerometer and the gyroscope were both high range. We're preferring range to resolution here. Generally speaking, the higher range you go, the less resolution you get with these things, but we were willing to accept that trade-off. And the idea with the dual core setup was to essentially take a high priority task like running state estimation and reserve one core for that, right? So I'm not pinning multiple tasks to that core. It could just do state estimation. And then on the other core, I can take lower priority tasks that maybe only need to run a few times a second, like say sending.
So sorry.
You're good. Like say sending telemetry packets, or writing to Flash, bulk tasks, or things that don't need to run too often can be done in parallel or as several tasks pinned to one core. And of course, additional peripherals on board, surface mount, SPI flash. 256 megabytes should be enough, but it really depends on how much data we end up writing to it. And of course, a buzzer for user feedback. So implementation, really straightforward. It's a 4-layer front and back board layout. We could have easily taken up more space and just done the front, but I guess it looks bigger when you're designing it. And then I got it printed and I was like, wow, we did not need to do that. The problem with doing front and back is that some of the heavier components can be, tend to fall off when you're doing reflow. You assemble one side, you flip it over, you go to reflow the other side, the components fall off. So using a heat set adhesive on the components you assemble first was necessary. Regular linear power regulation, technically on like a 3.7 volt battery, it can drop below the 3.3 volts typically required by instruments or microcontrollers, while still being in an acceptable range, but you can sense the battery voltage with an analog to digital converter to detect, am I within my acceptable battery voltage range. And of course, a single USB-C connector for wired connectivity. So unlike an STM32, I don't need a 4 or 5 pin debug connection. I can just plug in a USB-C and call it a day, or USB 2.0, but I like C. And then of course, heavy components on both sides is a considerable problem when you're doing this. And if 0402 type components, so really small resistors, really small capacitors, are a pain to assemble. Forget anything smaller than that. It can be done, but your hands better not shake. So where are we at now? Basically, assembly has been where we're stuck. There's ongoing assembly issues, currently debugging those. But the lesson we're learning from that is maybe the single board approach was too aggressive for the first time around. Not having experience with assembly, introducing too much risk in that phase of the process, maybe we need to back off and introduce something more modular. We attempted hand assembly twice, both failed. Vendor assembly, not really feasible because they require minimums for boards, but we need to back up and reevaluate. Now that we know that there's considerable risk in the assembly phase, reevaluate our approaches so we can factor in the cumulative risk for every approach. And then if we adopt a modular design, say like that backplane approach I mentioned earlier, that will allow us to reuse instruments and reuse components without dropping $90 every single time we go to assemble the board. And that is pretty much where we're at right now. Thank you very much. Are there any questions? No? Cool, thank you.
All right, so this kind of concludes the stuff that we were going on the stage. I think, feel free to talk. I'd like to have a little picture for posterity's sake, if we can do that now, and then feel free to talk and disperse. We're likely going to close up shop in, I don't know what time it is, but it's 3 or so right now. What are you thinking? Potentially 3:30, I think, was when we were saying we're going to stop there. So we're going to stick to that. Thank you all for coming today. Really appreciate it. The podium presentations were super insightful, and I hope you enjoyed all the speakers. I hope you remembered the stuff we talked about in the very beginning of the day regarding safety and recovery. Stay safe, and I hope that you guys enjoy the rest of the competition. Thank you. So picture maybe at the